as we're recording this podcast, sun is bombarding Earth with 174 petawatts of energy. That number is so big, it seems meaningless. So let me put it this way. In the next 1 hour of this podcast, sun will deliver so much energy to Earth that it is enough to power entire human civilization for an entire year. Am I right?
Yes, you are absolutely right.
So yet we use just less than 0.01%.
Yes.
And I think that is going to change in the decades to come, because scientists like you are working across the globe to come up with new materials that can capture sunlight to the max. So in this episode, I want to go deeper, explore solar energy from first principles thinking. Then we build on top of that. I want to explore what's happening in the present day, how far we have come in terms of solar tech, and then the cutting edge, what's ahead, and what are you working on, and your life as a researcher, your journey, your discoveries, your failures.
Thank you, Clinton, for having me here. And you mentioned, I'm working on a cutting edge technology. I'm just a tiny speck in the whole cosmos. There are so many people working around and they are doing amazing work. And as Einstein mentioned, that we are standing on the shoulders of the giants.
Nice.
So I should say the same thing for me. So I've been involved with this field for some 9 years now.
Wow.
After my undergrads. I was fortunate enough, I would say, to be around some of the leading people in the country and some of them around the world. So I was just fortunate to be in that space. But yes, as you mentioned, the field of solar energy is really exciting. It's a good time to be working on those things.
Right.
I'd like to talk about all the aspects, all the good, bad, and the uglies, and also the challenges.
Wonderful.
And as a scientist, as a researcher, we are the problem solvers. So there are challenges, and how we are dealing with them, we'll discuss.
Before we get into solar cells, let's get into solar energy.
Yes.
The first principle when I think of solar energy is abundance.
Yes.
It's an
you're right.
abundant form of energy.
Yes.
Sun delivers 10,000 times more energy than humanity uses globally. So
That's
how do you
correct.
comprehend this number?
See, the life itself is because of the sun. Had there been no sun, there wouldn't have been any life on Earth.
Right.
So, even if we try to differentiate or categorize different technologies like coal, nuclear, and other things, but fundamentally, all of them are indeed solar, if you think about it.
Right.
Something gets fossilized over the years. It's
Sun
taken,
energy.
like the sun is the origin. Sun
How
primarily.
is exactly nuclear energy is from sun energy?
Okay, so to answer this question, and I'll try to relate it with our topic for today, photovoltaics as well. So the thing is, we'll have to go back, like how the earth even was created and how each and every elements were formed. So probably we will explore the answer to this question in that line.
Okay.
Okay, it might sound that I'm getting away from the topic, but believe me, just be with me for a while.
Right.
We are in the topic. Okay.
Love your
So,
energy.
yes, it all starts with a Big Bang, like the general understanding, at least the most established theory. There are counter theories as well. So after the Big Bang, there were matters and also antimatters people talk about, and then they annihilate. I'm not going deep into that because that's a particle physics. Probably you will contact some particle physicist and they will explain you
Right.
in a better way the
Right.
cosmology. But I'll skip everything, matter, antimatter, and then most of them got annihilated and we were left with only few things. And all the things we see around is the result of that few things. That's like one part in a million. So that was the extra gibberish or the garbage which was there in the early universe that the entire universe is made up of. Now there were two important things. One was the gravity, which was trying to bring everything together. But as soon as the things start to get together, when they get really close, there is another thing which is called gaseous pressure. So you have ever wondered why the things are round, like these things like Earth or the sun, why they are round?
Right.
Why they're spherical, I should say. Round is like more like a two-dimensional
Interesting
thing.
question.
Yes. Have
Why
you thought about
Earth is round? Why planetary bodies
Yes.
are round in nature?
Yes. I think I just mentioned few things, so it's in that line.
So they're all formed because of collision. So No, I can't.
Okay, so
think.
those two things, the gravity and the gaseous pressure. So the gravity is trying to bring everything closer, but the gaseous pressures, they are trying to pull them apart. So there is a limit to it. So the spherical is the shape where both of them gets balanced.
The
That's
equilibrium.
where equilibrium. Though they are trying to break it every now and then, but that's the stance they have. That's what made our sun. And sun is just like a huge, magnanimous powerhouse. What is happening there at the core of the sun? So it's basically the hydrogen, our first element. So hydrogen, they are just fusing into each other, and then they are forming helium. So that's the cycle. So during this process, some of the photons gets out. That's the light. That's what we see. That's bring out everything day and night and all the solar energy and the sun source. So I'm talking about the source. So basically, it's the nuclear reaction happening inside the core of the sun, which dictates what elements are about to get formed, which is like hydrogen getting converted into helium. Now here is the interesting part. Believe me, I'm still talking about solar cell.
Okay.
The interesting part is not the birth of the star, but the death of the star. But before that, suppose the sun is formed now. Now, because of the gravity of the sun, there were other objects which couldn't have their own light, but they just came in the influence of the under the influence of the sun's gravity, and they started to revolve around them and also rotate in their own axes. Same things for the moon formation. So that's how we have planets, and it goes for the other exoplanetary systems, other sun systems as well. I mean, star system, I should say. So that's how it's building up. So basically, now we have a sun and the planets going across. How those planets were formed, that's related to the death of the star. So there is very cool pop culture thing regarding this, like the death of the star. Do you have any guesses? You switch on Discovery. Exactly, yeah. So actually that is related with the death of the star.
Right.
So there are three possibilities the way a star can die. The first one is it can form a dwarf planet. The second thing, it can form a neutron star. And the third thing is, you rightly mentioned, the black hole. So what happens when a star dies? There is something called supernovae explosion. What happens is that which star will form black hole will depend upon its size, which is called Chandrasekhara limit.
Right.
And which was discovered by an Indian scientist. And it's a very cool story.
Right.
He discovered that thing while he was on board. He was traveling from India to Cambridge. He was just 19 and he made all those calculations.
Wow.
And he got
When
Nobel
he was
Prize.
19.
Yes, but
Wow.
he got Nobel Prize for that way later, like many years later, because some of the premium scientists of that time did not believe it. But indeed, it's called Chandrasekhara limit. So only the stars, which are 1.4 times of the sun, can form a black hole. Now,
So sun can't form a black
sun
hole.
cannot form a black hole. Yeah, right. Yeah, I was coming towards that.
Okay.
So what will happen to sun? Any
Neutron
guesses?
star?
It may.
Oh, no. Our sun will become a dwarf star.
Yes.
Okay.
There comes a time when the gaseous pressure wins over the gravity. That happens when all the fuel that the sun started with, which was hydrogen, got converted into helium.
Sun is left with no hydrogen.
Yes, because all of them is converted into helium. And paradoxically, the more fuel a sun starts with, say hydrogen, sooner it will die.
Interesting.
Because it's just like a wildfire. Okay, so like bigger the fire, it's like the more fuel and it's burning itself. So the moment the sun is born, it's actually burning itself.
Right.
So we are good that sun will last for, I think, around 4.8 billion more years before it will start,
before sun dies, I think it will engulf Earth as well. That's another question.
Yes.
But humanity would be another planet.
Yeah,
Mars,
probably your
right.
podcast will be stored somewhere in some other planet, maybe some other galaxy.
server
I
in
hope we don't
Mars.
lose it. Yes, maybe beyond Mars. Who knows? So yeah, coming back to that point, like the death of the star. So when the star dies, all those things, there's a term for it called red giant. So basically what is happening, it's an analogy, but it's just like a volcanic eruption. That's the sun is like burning things, some magma coming out. So it just flows. So that's when it will consume its planets and all other things in its vicinity. That's how the Earth will also die. So that's the thing. So here we have a one-step or two-step reaction, like hydrogen is getting converted into helium. Now coming back to your question, how the nuclear energy is related to sun.
A whole different journey, but I love the journey.
And also it will lead us to other very important thing as we are going to talk about different photovoltaic technologies. So the thing is, I mentioned a few minutes back about the supernovae explosion. It's the supernovae explosion that's where the different elements are formed. Now, we are talking about the slightly bigger stars, bigger than the
sun.
Larger the size of the star, the more intense that burst will be. It's just like a cracker. So like that's why it's called explosion. So there are supernovae explosion for bigger stars. It's also called hypernovae explosion. And there are many associated phenomena. So this is just the basic. I'm not a cosmologist, though I am interested in cosmology. But yeah, I'm not a professional cosmologist. But that's what is happening there. So, but why this is important? It's because that's when all the elements are getting formed. Depending upon the intensity of the explosion, this reaction, like the formation of elements will go on. So hydrogen is getting converted to helium, helium to carbon, carbon to nitrogen, nitrogen to oxygen, oxygen to iron. So that's one thing. Now I'll ask you another question.
Yes, very interesting.
Okay, so we have some elements with us. People go crazy about it. India is a gold fringy country. Like 12% of the whole world is the world's gold is in our Indian household. Okay, we love to collect it. Why gold is expensive than silver? Why platinum is more expensive than gold?
Scarcity.
Why that is scared?
Because atomic number is huge. Okay. That the reaction probability in the supernovae explosion is lower.
So you mentioned a very nice thing, which I wanted you to answer. Like you mentioned atomic number. That's the key thing.
Okay.
Absolutely right.
Thank you.
Were just, So basically the chain reaction, like the things which are getting formed inside the supernovae explosion or the hypernovae explosion, depends upon how big the explosion was. So some of them, the smaller stars will terminate at one particular element with lower atomic number. Say some reaction might go till just oxygen, just nitrogen. Some may end at iron, but it takes a lot more intense explosion for silver to get formed. Even greater for gold to get formed.
What is the highest naturally forming element we have on Earth?
Oh, I think that we can Google it.
Yeah,
so
very interesting question.
Yeah.
No, I think,
so that's why. So like it's related to the atomic number. So the highest the atomic number, the greater efforts it take or the more intense explosion required for the formation of those elements. So yes, all elements were formed because of the death of the stars.
Uranium. There is no element beyond uranium,
and uranium
which is naturally formed.
Uranium is what?
Radioactive element.
Where it is used?
Nuclear reactor.
You got your answer?
Okay.
So nice. There is this saying, you might have heard about it. It's from Carl Sagan and Neil deGrasse Tyson keep saying about it. We are all connected to each other biologically, to the Earth chemically, and to the rest of the universe atomically.
Right.
Cosmos are also within us. We are made of star stuff.
Right. I should do Surya Namaskara often.
It's only recently that we started working on this stuff that we can directly convert these photons into electricity. Electricity itself is a pretty modern thing. If you see the entire history spectrum, it just came like 300 years back, hardly. Interestingly, the first solar cell was demonstrated, or rather, it was a serendipity. I think it was Becquerel in 1839 or 1840. So he should be given the credit where he first saw something where the light was getting converted into electricity.
Right.
It's only after well beyond a century when the people started to take this thing seriously that it was indeed possible. And that happened probably because of our very lovable material that we see all around, all our electronics, all our things.
Right. Transistors, semiconductors.
Yeah, and what it is made up of. Again, the elements which was formed inside a dying star, silicon. So the first solar cells, they were made of silicon. Even what we see around, like whatever installed in our buildings, in our schools, colleges, everything, they are mostly silicon-based solar cells. One thing, why it is expensive, it's because of it's cheaper if you compare with the traditional way of electricity, but still it's not cheap enough, I would say, because it involves the same amount of processing, which is like getting a purest form of silicon, which can be used for the electronic purpose. The silicon, the source is the sand or the quartz, which is say 95%, 98% pure, but that's not good enough. To make an electronics, we need 99.999999
Wow.
at least. So it's called 9N. That much amount of purity we need that we can think about fabricating
So
any
silicon
electronics.
has to be that pure.
Yes. So now to achieve that pure silicon, energy intensive process, it's very expensive. That's the reason we don't see them around. Like if you say in India, why we don't have, forget about the photovoltaics for, I think recently in the last 4-5 years, there has been a lot of progress in this direction. Like people have been working and there are so many policies and other things. New fabs are coming up. So hopefully it's an exciting time. The coming decade looks like an exciting time in India. And with collaboration, like as a human being, we can talk about the world collectively.
Right.
Because if something gets discovered somewhere, it gets propagated.
So you're saying it's not about efficiency, it's about manufacturing difficulty.
Efficiency matters, but also to reach that amount of efficiency, what is the process cost? So it requires a lot of stuff. So firstly, we need to purify it. So there are certain processes. There is one very popular process called Strzelecki process. I'm not sure whether I have pronounced this correctly. I think it's a Polish name. So it's called CZ process or CZ process. So that's a commonly known process. And then there are some chemical purification there are step-by-step things. And so it's energy intensive. And the thing is, it requires clean room. We should have a minimum amount of dust particle. Because ultimately we want purity. To get those things, it requires a lot of capital.
Right.
Lot means lot. I think I have few numbers probably that will make that conversation more crisp rather than just rounding about.
Right.
Yeah. So this is what I'm talking about. Probably you can see this. If you can see it here. The facility construction itself required 500 million to 2 billion.
Whoa.
You see that? So, and it depends on the capacity. What's the wafer size? Wafer is our substrate where we will build everything. So now you see the point. Why we don't see them around. Why we couldn't capitalize yet. Because as a country, we had other priorities and where we could say. So that's the primary reason.
Right.
So that's the first bottleneck. Other things are pretty much okay once you build the facility. Then the growth process I mentioned. So this growth process is very interesting.
What's growth process?
Growth is it has to form a single crystal. That's when we get a pure form. We further pure it with some chemical procedure. Ultimately, what we get is a huge cylindrical rod. That's what we call silicon ingot. So first we need to have facility. Then we need to perform this process, which requires high temperature and capital. After that purification, then we slice them out. And eventually we purify it further by polishing it. Then we get those wafer. And then we can fabricate things like integrate designs to get our semiconductor or electronics working. Right. So that's what is happening in the fab. Talking in a very layman term, earlier the computer used to be of this room size.
Right.
But now
even this big room size is
our
to show
phone
5
is so powerful.
GB,
Yes.
5 MB of
5 MB. You might have seen that photograph.
IBM.
Yeah, IBM photograph.
Right.
Yes, yes. So, but now our phone itself is so powerful and it's just changing. It's going to change even further.
Right, right.
What has happened?
The number of transistors in the area doubles, right?
So interestingly, there is this thing called lithography, which is nothing but like how you write something on a stone. It's a very old practice, like things written, inscripted on a stone.
Right.
So it's basically that writing, like how fine we can write.
Wow.
So previously it was in micrometers, then it turned out to be nanometers, like 300 nanometers, like how clearly, how precisely we can write. There are different methods. So like including laser and then developing those patterns. So that's the entire process, fabrication process.
I love humanity for this.
Okay. So
crazy.
How fine we can write, that defines our size of the things.
Right.
It's just like...
Now we have gone to the Armstrong level.
Not
in terms of lithography.
Not angstrom, but 3 to 4 nanometers or 10 nanometers.
Wow.
But you see, it's like earlier you were writing with a crayon. Now you are writing with a very fine pencil or even finer things. You see my point? Like, so we made those advancements. Now how these things are done. Now you see the point why these facilities are so expensive.
Right.
Because you need control environment. Imagine a dust particle which is of we have dust particle of some several hundreds of micron size, and the things we are dealing with are nano.
Right.
So it's a giant for it. It's like 1,000 times more. Even one dust particle.
It's like a sun for Earth.
Yes. So you see the point.
Right.
That's why we need that facility. So that's what it is called, clean room.
Clean room, so fine lithography.
Yes.
Integration. So material purification, many things in manufacturing play.
Yeah.
And that's why manufacturing is expensive.
Yeah. Then probably I should quickly talk about the different kind of solar technologies. And we started about it and we have been talking about silicon for a while now. Now there are generations of solar cell. Okay, so the first one were the... in fact, I have a picture. I'll show you very quickly. So there are basically 3 generations of solar cell. The first one is the wafer-based, which includes like monocrystalline or polycrystalline. Crystallinity means how pure something is, like long-range order of atoms, how atoms are arranged. It's like whether students are standing in an assembly line or they are playing sports. So if they are playing, they are amorphous. But if they are made to stand with a one-hand distance, so it all looks uniform from all the direction. So that's the crystallinity. There are complex structure. So you can see that continuity, like the patterns which is getting repeated. So that's the crystallinity.
That matters for the efficiency.
For everything, for the electronics. Achieving that increases the cost. But coming back to it, those are our first generation, wafer-based. Wafer is what? The same ingot I talked about. Like
right.
You manufacture that thing, you cut them, polish them, slice them, you get it, then you fabricate it. Luckily for solar cell, we don't require that nano patterning because we need larger surface area to manufacture solar cell. So I would say the solar cell processing is relatively easy. Then the mainstream electronics, like our gadgets and other things, the transistors. So in that way, but we still need silicon wafer, which is expensive because of the processing. So all our the first generation solar cells were made up of these kind of material, which are very good, highly efficient.
How much efficiency we are talking about here?
25%.
Wow,
even
okay,
more than
not
that.
bad.
That's what we see, even in space and other things. Wow, but they are very expensive. That's why they are not commercially available.
So we monocrystalline.
Yes.
Okay.
Yes.
Okay. Now I got it.
So
we find in the space satellite solar cell, no?
They are more complex. I'll talk about it.
Okay.
We are heading towards.
Nice.
Yeah.
Nice.
I'm glad that you asked such a question that I could build upon those things.
Okay.
So that's the first generation solar cell. Then the second generation solar cell, people talk about, we can make 25%. and it's crystalline. But what's the use? It's so expensive. What's the point if I can make a car of 10 crore? It's fancy, like 177 Aston Martin. It's good, but it won't work in Indian road like in any other way. Like it's good to have those things. So it's that kind of stuff. So we refined further. Like we sacrifice efficiency a little bit, like compromise and that part. But we can get something like what is pretty much practical. So then we have these thin film solar cell, which includes something like amorphous thin film, cadmium telluride, and copper, indium, gallium, selenium.
When did this happen?
Timeline, I would say around like 80s, 90s. Yeah. So the second one were less efficient.
But more
the thing is,
affordable.
like we sacrificed on the crystallinity, but we don't have to work that much to achieve like that, like obsession with the perfection and just spending
because efficiency
dollars.
isn't main the concern. It's affordability first.
Yeah. Now we have reduced cost. Can we keep on reducing the cost further? So there is so much we can do with this, I would say, inorganic material based on germanium, selenium, silicon, but we don't care in some applications like space. So because
there is efficiency is the much
efficiency is
concern,
the most concern. So we are already in the second generation of solar cell where we have compromised on the crystallinity and we are there affordability, and we could make them thin. With making things thin, give them conformality. You see my point? We cannot bend this table, but we can bend this paper. Why? Because this is thick, that is thin.
Because of they were amorphous in nature, so we can bend. Crystalline would break, so amorphous have a flexibility kind of thing.
That's one thing. You are absolutely right. That's what we could make slightly flexible electronics kind of stuff starting from the second generation, but still it's not very flexible. There is a limit to which you can bend it.
Okay.
But the other reason is the thickness. Thinner the thing is, it's easier to bend and other stuff. So that's another reason.
Okay, let's come to the third generation.
Third generation, yeah. Now we are talking. This is a technology we have been working
on. Okay.
And that includes starting with the organic solar cell. So they are the sister technologies. So it started with the organic solar cell and the several other technologies. And then we have entire family of them like dye-sensitized solar cell, often called the Grechel cell. So there's a famous scientist.
Basically?
As the name mentions, we have moved away from the traditional material.
From silicon to other things.
Organic. So
carbon-based.
Yeah, carbon-based. Yeah, you are right.
Wow, okay.
So carbon also has a valency of 4. It's just like silicon.
Right.
So basically, it has that capacity. But if we think about carbon, what's carbon? It's an organic thing. How can that even be conducting?
Right.
So that's what has happened. Like there is a Nobel Prize for this also to Professor Alan Heger and co. There are several other. It's possible to conduct electricity even in organic materials. So that's the discovery. That's like 90s, like late 80s and 90s. And in fact, the lab where I am in and the lab I work, it's called organic nanoelectronics. So basically we are dealing with this kind of electronics. There comes one more thing. Again,
it's like a polymer, right?
Yes, it's a polymer. Again, there is a thing, I must caution it, because often when somebody visits and hear it for the first time, it happens so that we are overselling it because it sounds so fancy. And I'll tell you, it will be even more fancier what if I told you that you already use this technology?
Touchscreen?
You're close, but why? OLED TVs, OLED screen. Okay, so it works. We have it. So we already have that technology.
Even that quantum dots, those things, right?
Yeah. Right. That's also the third generation one. Oh, right, thank you. Thank you for mentioning that. It just slipped my mind.
When you said TV, quantum dots I'm quite aware of. Even Samsung marketed quantum dots.
Yes.
What are quantum dots?
So dot means it's like how a particular structure is defined. Some structure can be 3D. Some can be 2D, 3D means 3D structure, 2D means X and Y.
Right.
Then there is line, which is called 1D. Then if there is some dot, then it's called 0 dimension.
Right.
It looks all the same.
One
And it has to be like in nanometers. So those are the dots. So how those things are arranged will give certain properties that we can use it for our benefits. So coming back to that point, I don't want to oversell it because there are certain limitations. But the good thing is they are conducting, and stability is a problem that has been a problem. But nevertheless, people have worked it out. The example is the OLED TV. So like the problem solving, that's where that's what we are trying to do. Like in PhD, in industry, and other things, we need to find this. Find this solution to these problems. By the way, all the material has some limitations. So there is called limit, like how much it can give. Like in terms of silicon, it's called Shockley-Quasar limit. There's a term. Don't worry about the terminology. But it's important if you are studying. We have to like what are the losses. Like how things are balanced. It's like nothing is 100% efficient. Now we can make liquid solution, like we can dissolve in some material and we can make ink kind of stuff.
They can convert solar energy into electric.
Yes.
Liquid form.
Yes.
Wow.
That's how it all started.
Well, when was that advanced breakthrough happened?
That happened in it has been going on like 80s, 90s, 2000.
Nice.
Lots of development.
What are they
2000.
called? Such type?
Organic materials. That's the third generation field is. Precisely we are talking about third generation. Then there was like 3.5% through those initial materials. But then there are several material. For very long time, it stayed till 12%, 13%, which is okay. Because now you see the difference in terms of cost. Earlier you required this big giant factory, billion expenditure. Now what you require? Your magician, the chemist magicians have made those molecules. You can dissolve in a solution any regular day in the lab. That's what the field is all about. You know, and it's all related. You see, so that's the ink has the capacity to make that photoactive material. Now, how to process that ink is the other thing. Unlike the silicon wafer, now we have inks which can be made into thin films. These films are very thin. Like for organic, it's just 80 to 100 nanometer.
Wow.
And they have high absorption coefficient. Like even with that small thickness, which is better than the silicon, even with that smaller thickness, they can absorb the required amount of light that can be converted into electricity. So that's organic. Again, then the second thing is the dye sensitized solar cell. Which has slightly different mechanism where instead of this organic molecule, there are some dyes, which basically does the same purpose. So they remain in the dye form or slightly liquidy form, electrolyte form, and then this electrochemistry happening between the two like the electrode system. That's when we get. Okay, I'll explain the electrode system. So I think this is the right time to understand about the structure of any solar cell. First thing what we need is the photoactive layer, which converts light into electricity. So once a photon gets absorbed in the active layer, it generates exciton. Excitons are nothing but electron and hole pairs. Okay, so now it's our responsibility to collect those electrons and holes before they get recombined. So those electrons and hole collection, that's what we say that we have harnessed the electricity. So like the photon, that material has the property of absorbing the photon and then generating electron hole pairs. Now it's our task to collect them
before they recombine.
So, before they recombine, absolutely. So basically,
what happens if they recombine? It forms a non-charged particle.
Okay, yeah, a very good question. If we don't collect them fast enough, there is a time. There is a time, it's called relaxation time, that it should be collected. If not, they will recombine. If they will recombine, it's a kind of loss. Now there are series of losses. Few losses are called radiative losses. The second one is non-radiative. Like radiative means something is radiating, like light. Yeah.
Photon is emitted.
Which is happening in LED. We want that thing in LED, but we don't want them in solar cell. So that's the thing.
So that is a radiative loss. So what is non-radiative loss?
Heat and other stuff.
Okay,
and then there is a like detailed and complex physics. Probably that's beyond the scope of our discussion. So
okay.
that's what we study. By the way, if you want to do
So now
research,
you have
that's
to
a thing.
connect the electron and hole pair before it recombines.
Yes,
So
recombines.
how would you do that?
Yes, very good question. That's when we need to have other layers in between. So we have the active layer at the center, and we have electrodes. So one will collect the electron, other will collect the holes, but in between we will also place hole transport layer and electron transport layer.
Okay.
If I can draw it here. So basically we have our active layer. Active layer is like any material, like silicon was the active layer, organic was the active layer, DSSC is the active layer, quantum dot is the active layer, and the other technology we are going to talk about is just the active layer.
Comes in.
Yeah. It would have helped to just have one electrodes with certain properties, like one which can collect the holes. So holes will be collected in one of the electrodes. And so electron is negatively charged, so it will go towards the positive electrode. Like that's how naturally they will move. And the other side, we assume the vacancy will move, that the holes will get collected.
Electrode for the holes.
For the whole negative electrode, because they are positively charged, so they will attract to it. Now, to make this thing more efficient, we often introduce hole transport layer or the electron blocking layer. All these things happen in a nanosecond or picosecond or even femtoseconds in some cases. By the way, we have characterization tools to precisely map them, like how fast or slow the processes are.
It's really crazy.
Okay, but these things are happening at this nanosecond or picosecond level.
Very short fraction of time.
Yes. So these are the materials which inherently they cannot capture the light. So they are not photoactive, but they have electrical properties. They have their own conductivity or certain properties that will facilitate.
Like
they can extract,
repulsion or attraction. Okay.
So they can accelerate those processes. They can enhance those collection. There could be n number of layers. That's what the device engineering is.
Wow.
And precisely that's what my research is, and that's what I am doing. So I designed these devices to get more efficiency. Specifically, I work on perovskite, and that's what. Let's get into the perovskite. Yes. So they are the third generation solar cell.
I'll come to it.
Yes.
We'll cover the solar power. Swanson's law. I love that. Just like Moore's law, named after the founder of Sun Power, that says solar panel prices drop by 20% every time global production doubles.
Exactly.
Nice. Just like Moore's law, right?
Yes.
As someone in the field, does this feel like a real law of physics or just a happy coincidence?
As efficiency goes high in terms of materials engineering, all because of changing the material itself. Yeah, lithography precisely is not directly applicable in case of solar cell, because we still need surface. But say my solar cell is 10% efficient. For example, 1 meter square of area to generate 10% efficiency. What if the solar cell efficiency is 20%, which means that we'll be able to get same amount of energy with just half the area.
Right.
So that's how it goes.
So for every 10 years, that has been the case in the solar cell.
Yes, because the efficiencies have gone up. That means we'll be able to generate the same amount of power with smaller area.
You mean that has to do with the change in material research?
In material, optimization in material.
What is optimization?
Optimization means like from the same material, if we could minimize the losses that I talked about, like radiative and non-radiative losses.
Right,
for example, say for silicon, the theoretical limit is 33%, and we were able to get around 25%. So still there's a scope. Like if we could optimize it and push it further, that's called the optimization.
Wow, 33%. How did they come up with that number?
Okay, that's a whole lot of calculation. I can refer a complete set of paper.
Okay.
So where it's called detailed energy management. It's the same principle. It's like how much light is getting absorbed, and then inherently how much material can tolerate in terms of keeping it defect free. And also inherently there are few losses, like thermodynamic loss, like something cannot be 100% efficient. So there are always certain set of losses, say radiative and non-radiative losses. Then there are certain components of them. So we make calculation of each one of them and then come up with that number. So that number is there for
Okay, for
every
silicon,
specific
it
material.
is 33 is the limit.
Yes,
it can't go
it cannot
beyond that.
go. Single junction. Single junction.
What's single junction?
Single junction means just one material, one active layer. There is another thing which
okay. Multi-junction.
It's multi-junction or tandem.
So with that, you can go beyond 33%.
Yeah, but then the theoretical limit will be different again, because we can have the same kind of calculation even for that system, a new system. But definitely we can push that by combining two or more active layers or different composition of material.
Wow.
So that's what the tandem solar cells are. And currently they are deployed in space and similar applications. So they go as high as 45.
Tandem. Wow.
45 and 48% even.
Damn, 48%.
Yes.
Not theoretical, just practical.
Practical. So their theoretical limit would be around 50, 52. So the way we engineer these things can determine like how to make use of them.
How much it costs for 1 meter of such tandem?
Okay, that I'll have to calculate for silicon and like there are other like CIGS solar cell.
CIGS,
Yes. It's cadmium, indium, gallium, and I think selenium.
Wow.
I think
I
that's
love
what
the
it
fact
is.
that there's a variation of elements and how they perfectly, it's like an alloy for metals, right?
Alloy for metals, and also alloy is one thing where you mix certain ingredients to form one layer.
Right.
Then combinations of these alloys, like multiple layers.
Too
so
many
tandem means we have.
variations.
So you remember I mentioned the term active layer. Like silicon is the active layer, or organic solar cell is the active layer. So that's the single junction.
Right.
Those three combination. But we can have multiple of these layers.
That takes a lot of trial and error, right? To see which one works well.
Well, we can model it theoretically, like based on the physics, the way we calculate our theoretical thing. So there
are
are
softwares for that?
Yeah, and we can write codes. And so because the physics remains the same, it's like the material, what is the absorption coefficient, what is the thickness of the layer we are targeting.
Okay, that also
and
matters.
Then the amount of field or the photon flux which is coming into it. If we know them precisely, then we model like how much we should get. So every material has certain absorption coefficient, like what thickness it requires to absorb the amount of flux, light flux coming into it. And
flux is like intensity, right? Like number
and also
of
the number
photons.
of photons.
So,
yeah. So photon density.
Right.
And so we can model using these things. There is a popular method called transfer matrix methods. Like it's kind of generic. And then based on that, it's just the physics equations that we'll have to solve and come up with that.
That's how you do computation, and then you calculate and see if it's worthy to try it out, materialize these things.
Exactly. So there is this thing. So as we'll move further, so till now we talked about the generation of solar cell.
Right.
Different types from organic. In third generation, we discussed organic, quantum dot, dye sensitized.
Liquid.
All of them are made out of liquid.
Right.
And now what happens? Similar to the silicon manufacturing, like we get the wafer. So what was the ingredient? The ingredient was the silicon ingot, right? That was the starting thing. Here, the raw material is molecules, organic molecules that can be dissolved in certain compatible solvents. Once we have it, we again have the same kind of fabrication procedure. Here we use different substrates. So our substrate can be glass and
plastic.
It can be plastic, which is not the case with silicon.
Bendable, right?
Yeah, that's only possible with the third generation photovoltaic.
That means you can install it in the windows.
That's correct.
Electronic components, you can take them wherever you go.
Yes, window shield, facades of the building, everywhere you think of.
Right.
So we can talk about now perovskites.
Right.
Okay. So now what happened? All those people who have been working on organic solar cell and dye sensitized. So suddenly there was one paper in 2009 from a Japanese scientist. His name is Professor Miyazaki. And he showed that there is some dye which called perovskite, like with perovskite composition, it showed some photovoltaic performance. That was the year 2009.
There was
Right.
one revolutionary paper.
Yeah, that time nobody knew that's revolutionary. I find that paper to be really inspiring. Instead of claiming out loud like this is a big discovery or this will change the
It's
world,
like a breakthrough.
yeah, the scientist has just humbly quoted what research he has done and he has communicated it. Like in terms of scientific
Low
ethics,
key.
it's like, I did this experiment, I observed this. These are my results. So that was 2009. Then it turned out in 2012, the Oxford group, Professor Henry Smith group, who is one of the key persons and one of the pioneers in the field, he collaborated with Professor Miyazaki and they were independently doing some experiment on their own. And they found like there was certain composition, like this perovskite layer combined with other hole transport layer and electron transport layer. Wow, I'm liking it. Like we have already discussed the base, so it's easier to make it
Communicate,
understand.
right,
Yes,
right,
so
right.
the terminologies are clear.
Right.
So they were using one oxide, TiO2.
Titanium oxide.
Yes, titanium oxide. So they were using that oxide, and suddenly one day they got some really good numbers. It's like it was 3%, which was reported in 2019.
3% efficiency.
Yeah,
3%
4%.
efficiency was through 2009.
Yeah, Professor Miyazaki, Japanese group. And then in 2012, so while doing experiment like this, scientists got 10%. So they initially doubted because the material is just giving 3% and it was still the early stages. So probably the true potential was not yet discovered. With that, what I mean is the theoretical limit
Right.
wasn't known because it was a completely new thing. And then suddenly they thought that, okay, why it is coming? Probably it's because of some effect of TiO2 and other thing, or similar effects. It turned out they replaced that TiO2 with other material, they could still get it. Like by that time, they would have engineered it in a way that the collection was improved in nutshell. So there are multiple things to it, but that's how it got evolved. So that means that material has a capacity. So out of nowhere in 2012, a completely new technology, photovoltaic technology, unheard of till that time, it just came a boom. Because people, and those were the same kind of people who have been working with dye-sensitized solar cell and organic solar cell. So the stage was set. Right, so that's how the perovskite was born in 2012.
Right. Hype was created back then, 2012.
And it's a big thing because
reaching from 3% to 10% was a big
12%,
shock.
It was a big shock. Like there must be something because the people have been working with organics and it took some 15-20 years to reach even 12%, that too with inconsistency. By the way, perovskite, when I say perovskite, what is perovskite? Perovskite itself is not new.
What is perovskite?
Yeah, that's a very good question.
Yeah.
So probably we should discuss that a little bit. Any structure with ABX3 form. A is some cation, like positive charge, like entity. Then B is our central, say, anion. And X is some other element, say for mostly some, in perovskite case, it's halogen, but it could be anything else, like third entity. Now there are multiple, an entire family of perovskite. So one mineral naturally forming one is, say, this one, CaTiO3, for example. So here, Ca will become A, titanium will be B, and O will become X.
So calcium, titanium, oxygen.
Yeah, trioxide. This is an example of perovskite. But now it turned out there are multiple perovskites. Like there are oxide perovskites, there are halide perovskites, there are double perovskite, there are mixed anion perovskite, there are layered perovskite, this entire family. And then there is hybrid organic inorganic perovskite. The perovskite in solar cell, that's what we are talking about. They are the organic inorganic mixed perovskite. And they are made in a way that it can be used in electronics. So that was the discovery. That's what the shock, like something unheard of. And chemists have been dealing with it for quite a while. Classical perovskite is called methyl ammonium lead triiodide, which is CH3NH3 PbI3. So now if I say Pb is B, then what will be A?
There's a mixed one.
Yeah, CH3 and NH3 is A, absolutely. And what is X? It's iodine.
Hydrogen. Yeah.
Okay. So that's the classical perovskite. And it's theoretically it give around like 20 to 23%.
Wow.
And 21 is very common. Even in our lab, we make it like 20%. We can make it like 18 to 20%. Even I myself have made more than 20% with this material in lab. Having said that, yes, they are that simple that we don't need $1 million thing. Though still we require lab facilities. There are certain facilities that probably will also see them. So once we have those basic facilities, we can fabricate them. And we can fabricate them so quickly.
These are not expensive materials, you mean?
That's again a very good question. It comes back to our abundance thing. They are in abundance, these materials. So definitely their cost gets reduced.
Nice.
So that's one thing what makes them really cheap. One of the main advantages of this technology is the entire third generation, that they are really economical in comparison to the standard.
Easy to synthesize.
That means you can see, like, we don't have to rely on those expensive technology.
Wafers, manufacturing processes.
1000
degrees Celsius.
Yes.
Those things.
That's a very
Vacuum,
important point. Like, they can ease of processing. They can be processed in a very low temperature. In fact, many of our processes are just around 100 and 150 degrees Celsius.
Boiling water.
Yes. So the thing is, I already discussed the structure, perovskite, and layers. We can have n number of layers depending upon what we want to do and what our device engineering is. The way we had fabrication procedure for silicon, remember CZ process and other thing, we have the entire fabrication procedure here. Typically, it starts with any substrate. Say for example, glass. Glass is coated with ITO. Okay, indium tin oxide. Do you know what that material is?
Touchscreen?
Yes. So our conductive glass, our mobile phones.
Right.
So that's how we start. And we do patterning, like depending upon where we want our design. Let's not go deep into it, but basically we have patterning so that
glass and conductive layer on top of it.
Yeah, which is ITO, which is transparent, very important because we need light to pass through it.
Right. Okay. This is like
the photons.
Coating on top.
This is coating
on the substrate below.
This is glass is the substrate.
Okay, below.
Then we have certain procedure. Actually, it's called sputtering. We can do it in our lab, but to avoid complication, because it's an additional step, so people prefer to just purchase it commercially. Now then, there are certain processes which are common to other industries as well, like the established industry. They are called physical vapor deposition or chemical vapor deposition. So basically, they are the deposition techniques. We have some material.
How you deposit perovskite onto the substrate.
Yes. Those are the methods. So anywhere people use mix of these techniques. Now some of them are industry standard and some of them are lab scale. So in lab, one of the popular method is, or the most common method is spin coating. Spin coating is what? It's nothing but we take substrate, we place in a thing called spin coater, then we rotate it under certain RPMs. Depending upon the speed of the rotation, it will define the thickness. There are other parameters like what is the concentration of my liquid. So remember, we have our material in form of ink.
Right.
Now how we are depositing it? We are spin coating it. So that's one method. Spin coating is one method. Now deposition is another method. As I mentioned, chemical vapor deposition or physical vapor deposition. So physical vapor deposition is relatively more common that you will find in the lab. CVD you will find in more like confined spaces like clean room where their management is more. So each of these unit steps have their own stories. Okay, how they work, what is their functionality. But the net cell, they all help in coating one or the other layers of perovskite that I mentioned, minimum 3 or maximum N. Yes. So, but how they are coated, what methods is applied, everything is important. That will determine the quality of the films and the performance.
Also, right?
Even the thickness and the morphology.
What do you
Remember,
mean by morphology?
morphology is nothing like whether how crystalline, how ordered or disordered they are.
It's like monocrystalline, polycrystalline,
Yes.
same concept there.
In this solution thing, we have grains, like grain boundaries. You remember the cricket pitch,
Right,
how it looks. So if we do say SCM, scanning electron microscopy, we'll get to see those grains.
Patterns, okay.
Yeah, so they will be typically few nanometers, 300, 400
Why
nanometers
grains?
wide.
I mean, those matter in the efficiency. Is it
So-
to do with the direction of electrons pass through or something like that?
It's not just the electron. Remember, there are some molecules which are dissolved in a solution. So when they are spin coat, they disperse, they take up some space. Now there is another step called annealing, like processing temperature. So they are kept in things, say hot plate or oven, where they will start to heat. When that annealing process starts, they will start to settle down. The way they settle down will define the growth of these crystal or molecule. So there is this growth and nucleation. Nucleation means the island or like how it get together. So there is whole lot of kinetics involved. That's where the chemistry and physics involves, and how to tap it, how to control it. So that is dictated by our process. And this is the optimization step, like what to do, what not to do. And that's
you
the
do
research.
it.
First, a theoretical understanding, limits of the material, then the processing.
That's what you call morphology of the
Morphology control. So that's for one layer. See for all other layer.
Right.
Then we'll have to see layers compatibility. Like few surfaces can be hydrophobic or hydrophilic. Similarly, the solvents have their compatibility.
Right, and also
And-
they shouldn't react with each other.
Yes, yes. So otherwise they will consume each other.
They become different entities.
Yes.
later.
So now you see like how this thing proceeds. So that's the fabrication procedure. So if I have to take a classical perovskite structure, just to make the entire process look like simpler so that we can understand the other complex structure. Taking back the example of this methyl ammonium lead iodide. So the way it is done is we take glass, which is coated with ITO. So ITO is our one electrode, correct? Then we coat one whole transport layer. So classically, there is this material called PE.PSS. So say one example, or just whole transport layer for a while, we spin coat it, or we can use physical or chemical vapor deposition, or there is another technique called atomic layer deposition, ALD, which is pretty standard in industry. So we can use either one of them. For example, say I'm just using spin coating, very simple. I took the substrate, I spin coated it, first layer, annealed it for some time. After that, I coat the other layer, which is our perovskite, the main active layer. So there is certain recipe which has been optimized, like what concentration to use, what molar concentration to use, what should be the thickness, and how much it should be revolved, and then what should be the temperature applied and for how long.
Right. To get the right morphology.
Exactly. Okay. And then we coat the ETL. So ETL can again be spin coated with some
What's
material.
ETL?
Electron transport layer.
Okay.
Say for example, again I'll go back to the very basic structure. For example, PCBM, again a organic molecule. It's the same molecule which has been used with P3ST PCBM organic active layer blend. But here just PCBM component is taken and it is coated above the perovskite, which will facilitate the electron transport. That's why it's called electron transport layer. Then we have a top electrode, which is very important. So top electrode, we have metals, say aluminium, silver, and gold. So eventually what we had is at the center we have methyl ammonium lead iodide.
Right.
Then we have whole transport layer and ITO. And the other side we have electron transport layer and metal.
Conductive layer.
Yes. So those metal are also, all these layers are very thin. The active layer for perovskite is around 300 to 400 nanometers. ITO is 100 nanometer. ETL and STLs are typically, though they may vary, are around 40-50 nanometers.
Come up to 450, 350
Yes.
nanometers.
And then we have metal also, which
Okay.
is around 100 nanometers or 70
Within
nanometers.
500 nanometers would be the
Yes.
thickness.
Yeah. So once we get these things right, then we have this structure. And you see, we worked all this thing and it works. It gives 20%. Isn't it amazing?
Wow. Amazing.
Silicon with all these things,
Right.
it gives us that.
So much
and it's
Wow.
with so much ease. So that's the perovskite material.
That too with just decades away research.
Yes.
Decades back research. Just
Just 2012 and this is 2025.
20% research with the simple research step.
Yes.
Silicon has a theoretical limit of 33%, as you said. So is there a theoretical limit for perovskite?
Yeah, that is also around that, the sub 30, 32 for one particular kind. And
But you can overcome with the layering, is it?
yes. Oh, you're
Okay.
right. You're asking all sorts of right questions,
Okay, thank
which
you.
is like guiding us to where like we should be heading towards.
Okay.
So the thing is, this thing is clear, right? So that's a typical device
Solar
structure.
cell can't be layered. The advantage of perovskite over silicon based, one of the advantage apart from manufacturing is you can layer perovskite.
Yes,
That
yes.
It increases the
tandem.
efficiency.
Yeah.
That is tandem.
Yes.
Okay.
Yes. Yeah, we are approaching.
Okay, now I'm curious. What is the world record as per now in terms of tandem perovskite? What is the efficiency?
It's around 34%.
Wow. And
2025
is the
paper.
manufacturing is simple for tandem,
Not exactly,
but is simple compared to silicon-based wafer.
certainly, because
Okay.
it's just playing with all these things. So we'll go step by step.
Yes,
We are heading
yes,
towards the
yes.
right thing. So till now we have been just discussing the single junction, which is methyl ammonium lead
Right.
iodide.
Single perovskite.
Single perovskite layer. Now we can have different variations of them. Like we can introduce certain things in A site. We can introduce certain things in B site, and then we can introduce certain thing in X site. So let's talk about X first.
Okay.
So the X here is iodine. We can have other halogens, chlorine and bromine. Okay, what they will do, I'll tell you.
Okay.
That's one thing. Similarly, in B side, instead of lead, we can also have other things.
Before that, I want to understand. Okay, photovoltaic effect is simple in terms of silicon. I know photon hits and it will knock off an electron from the silicon atom. What happens in the perovskite? What happens when a photon falls onto
Yeah.
a perovskite? I want to understand that mechanism
Exactly.
first before I get into.
So the mechanism remains the same because the physics is same. Ultimately,
Okay.
photons are incidenting on the active material,
Which
photoactive
is A.
material, which can be like silicon or organic or perovskite or dye-sensitized.
In terms of perovskite structure, is it A or B or X?
So this is the structure of the perovskite I am discussing right now. So when it comes all together and we have a series of it,
So center one is A.
is the methyl ammonium CH3NH3, which is
and
the
blue
bigger
one
atom.
Is the X.
Yes,
And
which is
yellow one is
iodide in
B.
yeah.
Okay.
Yellow one is the this B.
Yes.
So when we have the continuity of this structure and we have a film morphology, that's when they become an active material. And there is one more term which is very important to consider: band gap. It's the energy band gap. Like the photon will have a certain amount of energy, then it should it should cross that barrier
Threshold, right?
threshold. So
Right.
so every material has some band gap. So especially if we think about metal, insulator and semiconductor, and what's the difference? Like metal, there is no band gap. It's a continuous sea of
Right,
electron
right,
because
right.
they are close to each other.
Easy to knock off an electron.
Insulator, why wood is into insulator? Because the band gap is huge.
It's hard to knock off an
Yes,
electron.
yes, it's huge. It's like 6, 7 or even
You need a
an
laser or
infinity.
something like that to knock off
Yeah,
an
even
electron.
then it will burn or probably never cross. Then we have semiconductors, like somewhere in between, like silicon and germanium, it's 1.2, 1.3. This particular perovskite, it's 1.55 electron volt. Say for silicon is 1.1, 1.2. So this one is 1.55 electron. So it's close to silicon, as you can see. So that means there are certain solar cell parameters. Okay, I'll mention two of them straight away. One is the short circuit current. Other thing is open circuit voltage. Very simple, the current and the voltage, like which will dictate amount of power that we are getting out of our solar cell. We need both of them to be high in a solar cell, but there is a paradox. To get high current, the band gap should be as low as possible.
Right.
and this is a very important conversation if you want to understand the tandem. So, and it's a property of all the materials, the silicon and this thing.
Right. Basic electronics.
We are talking about perovskite since you asked the question regarding the perovskite. So this particular one, in comparison to silicon is 1.1, 1.15, and perovskite, this particular 1.5, say 1.5. Now, in order to get good current, this should be as low as possible. But to get good VOC, the band gap should be high.
In order to get a good
open circuit voltage.
Okay.
So in order to get good, we need both of them, like current and voltage to be high for an efficient solar cell. But in order to get good current, our band gap should be low. But as soon as we start to get low band gap, we sacrifice on the VOC part. So we'll have to reach a sweet spot where we get good amount of current and we also get a decent amount of VOC. Now, we can play around. We can tune the band gap, which is not common in silicon and other things. You know how?
Tune the band gap.
Yes, exactly what we were discussing. Suppose ABX3, we can have chlorine or bromine or why not just this? So what will happen if we keep everything as it is? Instead of iodine, if we add bromine, the band gap will be 2.3. So as I mentioned, now band gap is high. That means I have a huge window for improving by VOC, open circuit voltage. But then I will sacrifice the current. So the current, which is typically around, say, 23-25 milliamps per centimeter square in case of methyl ammonium iodide. When I change iodide to bromide, the current is just 3, 4, 5 milliamps. So I just, it's 1/5 or 1/6. But I get voltage enhancement. Like if the voltage was, say, 0.91 volt, now I can get 1.6, 1.7 volt, 1.5.
That happens in the tandem.
Yes.
So one layer you play with the voltage, another layer you play with the current.
I think you have read about it. Yes, exactly. That's how it works. So that's the engineering goes. Okay, so that's one thing. So, and you know what? There is one another very, what I should say, aesthetically appealing element to it. It's not just the band gap which is changing. Physically, their colors are also getting changed. So this layer with 1.55 band gap will be yellow in color, whereas bromide will be orangish in color. And just by fine tuning the ratio of bromide and iodide, we can have mix.
It's like a colored glass.
Yes.
Okay.
So we can have bromide and iodide mix. We get entire different spectrum of color.
Wow.
Just by changing this.
Like one of the reasons why people don't have solar, because it disturbs aesthetically the roof
exactly,
things, right?
And it's just
right.
But so that limitation is not there anymore with these materials. It's fun to work with.
So you can personalize your color.
Yes.
You tell me your favorite color is blue, and you can synthesize blue perovskite.
Kind of like if that parent material has that element, but up to a certain extent, yes, even green, yellow, and other kind of thing.
Like if perovskite becomes a commercialized material or consumer thing, there would be a time, just like how you choose paint for your walls.
Exactly,
like
precisely.
Paint, manual.
Yes.
So what kind of paint what kind of perovskite you want, something like that, right?
So, like in organics, I was mentioning green, red, and other things. So there are organic molecules which have their different tones. So that advantage we had even in organics. In perovskite, we have these gradients like from red, yellowish, and other thing, and we can choose as you mentioned. And then
does playing with colors affect the efficiency?
Of course.
Okay.
Because we are changing the band gap.
Right.
We are changing the current and voltage output. So the efficiency with this structure 1.55, I was getting 20%, but now I just get 4-5%. But it's okay if I'm increasing. So it may not be a prudent way to go ahead to have a single junction with just bromide, but it will have application somewhere else, which is tandem. I mean, since we are already discussing about it. Similarly, we can make adjustment to the middle thing, which is the lead one. We can replace it with tin, certain proportion of it. Again, there are challenges to it. We'll come to that later. But we can play with that, and we can play with the cations. Currently, it's just the methyl ammonium. A very common approach is to replace it with few more cations. Add certain amount of cesium to it, or fermadinium, Fa. So now I have triple cation perovskite solar cell, which is the kind of standard nowadays. So we have certain amount of cesium, we have certain amount of fermadinium, Fa, and then we have Ma. And then we can have lead and tin certain amount of ratios. We can make solar cell specifically with just one of them. Now you see it's just like a chessboard. You have pieces and you can have infinite possibilities.
My God, too many computation.
Yes. There is this thing. There is a chart from NREL. NREL is National Laboratory in US, which certifies these cells, and they do all sorts of research. Even they have collaborated with NASA. They have actually sent perovskite solar cell into space.
Wow.
And I happened to meet one of those scientists. Actually, I met him twice in two different places. I first met him in Valencia in Spain in one of the there's a conference
called HOPD. What was the
HOPD.
efficiency of that cell?
That wasn't explicitly mentioned, but the purpose of that study was to understand how they degrade under those space conditions. Basically UV light and other thing, and how do they survive. Coming back to NREL, so as you can see this chart, so there are all those technologies that have been discovered so far. So you can see there are cells even for more than 48%, as I was mentioning. So this is the exact data. And it's a hard work for the people. It's just like a scoreboard because it keeps changing every day, I would say. Especially with perovskite and different compositions. So, but these are the perovskite in nutshell, where perovskite solar cells are placed in this category called emerging PV. So they are this yellow dot. As you can see, it's written 27%. So that's the record. I think it's some 27.23 now for this, which is triple cation, lead, and some composition of bromide and iodide. So that's the state of the art, which is 27%. Now, very interesting thing is, if you look back, it just started in 2012. Can you see any other technology which has grown so far?
It took them a long time to reach that efficiency.
So this is the fastest ever developed photovoltaic technology. You know, I had this moment. I was in Seattle this year in April. You know, the story of the first solar cell that I talked about few minutes back, Professor Miyazaki for Japan. He was there in the room.
Wow.
I was awestruck. It was such a fan moment. I was sitting there. I'm working in that field. The person who would have done the first ever experiment, he was there in the same room with same curiosity. Yes, I happened to talk to him.
Nice.
He was old, close to, I think, definitely more than 75 or around that thing, but that doesn't matter. And his enthusiasm was infectious, I would say. He was still asking questions. He was saying, he was curious about the young people. All of them were young in front of that. So that's amazing. Some things that we read in books, say Newton discovered gravity, but say you are among those people and other things. So that was pretty special, I would say.
Nice.
And then being within the community where people discuss about what's happening, and there are so many things are happening around, but precisely this is what is being done. Different composition, different alignment, searching new material.
Scientists are trying to find the right alignment, right composition. Trying out different X. And find efficiency.
What is the corresponding efficiency? I think
it's like playing for the world record, right? Who breaks the world record?
Exactly.
So present is 33%. What's
34 is the for tandem, 33, 34. 27 is for single junction. Even with single junction.
What was the composition for the single junction?
It's a cesium, Fa and Ma.
Okay. This is 27%.
It is 27% in just 12 years.
Decades of research.
Yes.
How optimistic are you? How far it can go?
Okay, so
with the single junction.
Personally, I'm very enthusiastic about the field, and given the fact that it's transferable, it's compatible with other layers, that we can add other layers and make tandem. So I am very much optimistic. But again, I should be, I should see it objectively as a scientist also. So there is an encouragement, because sometimes we read in the news that something has become this is very interesting, and we just hop on. But then there are other aspects to it. One of the very important aspects is the stability. What if I get this 27% but stop working after 5 minutes? There is no use. All those silicon panels which have been deployed, what we see on the rooftops, they will be just 12 to 15%, but they can last easily 25 years.
Right.
Okay, so there is stability. But for this particular structure, the starting structure, the stability was very poor, like few hours.
Okay.
Or after optimization, few months. But now with this triple cation and other things, they have been shown to even improve on that. From the cells which used to last only few minutes, now there are cells which last for 10,000 hours under harsh conditions.
Wow.
So then there is this entire thing, which is also partially part of my research to understand the stability of this device, because these are the challenges. So the stability, like now, why they are unstable? You may ask this question.
Yes.
Because they are very sensitive towards the ambient. Why? By ambient, what I mean is that we have certain amount of like moisture, oxygen, even light. They degrade. There is a reaction happening under the presence of oxygen and light, which decomposes this entity. Like the perovskite structure doesn't stay as perovskite.
Architecture is broken.
Yes. So because these are ultimately molecules, these are ions, plus, minus. So they leave their crystal lattice. There are two ways. One is intrinsic and other is extrinsic. Intrinsic means that's the physical limit. Like how they behave, what's the chemistry. That after a point we cannot avoid. We can manage by layers and other things. Reducing the defects means compatibility between the layers, how efficiently the charges are getting collected. Other thing is extrinsic. What if it's just like we can get wet if it's raining, but we can use umbrella. So there comes a thing called encapsulation. Encapsulation means just putting a cap, providing a protective layer. If it's transparent, so up to some extent we can avoid moisture and oxygen intake. So that's entirely a different area of research where people just focus on the encapsulation part. Stability, encapsulation is a part of stability.
Right. One of the ways to make it stable.
Yes. Encapsulation is the extrinsic stability. But then there are other things, like for intrinsic, that's the management. Again, coming back to the basics, first principle. What are the chemistries? What are the redox reactions happening? Ultimately, it's also like of chemical cells, like lots of chemicals are confined within 2 electrodes.
Yeah, perovskite cracked efficiency, but it has to do more with the stability, making it more stable.
Yes.
That's where more research is focused on, you mean?
Exactly. And substantial results have been achieved, like successfully stability has been managed to have certain level of control, because as I mentioned, the earlier solar cell would last for only few minutes, but now they last for thousands of hours. So there has been a substantial progress, that I must say.
With the
Encapsulation and just adjusting these composition. Even they make it more stable, like the triple cation ones are more stable. And also there are two ways of doing it. One is called PIN and another is called NIP. Just to make it simple, one is inverted structure and another is regular structure. The terminology is based on which layer comes first. It's like if I have ITO, which collects basically the whole. If a whole transport layer comes first to it, then it becomes a PIN or a reverse structure device.
You play with the layering.
Like where you keep STL or ETL. It depends on that.
Why would it influence the stability?
It does influence the stability. It's because from which direction, what particles, what entities are getting controlled, like getting trapped.
Interesting.
It's just like when we construct house, we can have gate from one end, but the orientation is important because the other lane might have something different. It does affect. Okay, I'll take example of metal to keep it simple. If we have whole transport layer just before the metal, then it's called NIP structure, or it's called the regular structure for the terminology. And if we have electron transport layer just below the metal, then it's PIN structure.
Inverted.
Yeah, inverted or PIN structure. So traditionally, like till 2016-17, PIN used to give lower efficiency, and NIP was better because of the discovery of some of the transport material, which were oxides like tin oxide or
There is also
TiO2.
discoveries happening in the material.
It's complete. Somebody would have used something long back. Like,
so there's discoveries at each layer.
Yes.
And orientation of each layer.
just imagine
Crazy.
the amount of people and the different backgrounds are involved in.
Right.
And they are just working, and it's entire libraries now of the material and material
it's like
composition.
mining Bitcoin. Like so many people are trying to mine, but one would get it right. Like something like that.
Yes. And also it helps the community if
Right.
one does it.
Data helps, like what not to do.
Yes,
like, you know,
yes. And
something
also
like
these efficiencies are certified, like NREL, or there are
that. So
other
you
agencies.
send your samples to this lab.
If I break the record, nobody will accept it unless I certified. But most of the time what we do, it's difficult to break the record, but still there are lots of fundamental studies that can be done. Say I won't be able to make 27% even if I follow the same paper, because it depends upon the environment. Now we are getting into the another territory, and we have crossed 10% of our like agenda for today.
Right.
More with this, it's like reproducibility. This is again a challenge. Like if something is made in one lab, how well it can be replicated. So science should remain science irrespective of where it is made. But then again, in fact, there is a paper. It's called it's like the trouble of getting the same device twice.
Right. I mean, if you standardize everybody's lab for perovskite, you mean still there would be
Ideally,
problem with the
no,
reproducibility?
there shouldn't be. As we will see, there is this thing called glove box where we process things. So their condition gets changed. First thing is amount of oxygen and moisture, and also how internal pressures, solvents, if there are any,
Damn.
how they affect. So these tiny things, because they are so sensitive. And even within those layers, we dope a little bit. So they are so sensitive that it can affect.
Oh, even impurities play a role, right?
Absolutely.
There. Okay,
so that
okay.
even who is making the device, that also plays a huge role. Suppose like if I've been making this device for 3-4 years, and there are certain steps, like I simplified it, like making perovskite is not just one layer, it involves another thing called anti-solvent treatment, like in the lab process one. So I mean, there are things, but I think
reproducibility is
a challenge,
another challenge.
but it can be minimized. That's what is called the optimization.
Okay.
So when we publish paper, it cannot be just one cell. It needs to be multiple cells. Statistical data, say around 30-50 cells we should show. Then we can show our maximum, but then we'll have to show our mean and the standard deviation. We'll have to.
So mean is considered for your record.
Yes.
Okay.
No. Record can be the first one if it is certified. But say if I come up with some composition, because there are, even in our lab, we have people who synthesize the material. In fact, we have some unpublished work as well, which has showed, which has worked equally with the standard things in terms of one of the transport layers. So say if it breaks the record, say for example, it's just an example.
Okay.
Though I couldn't break the record. I wish I could have. So, but yeah.
How much is your max efficiency?
Okay, so here with this kind of material, the first order, I was able to get around 20.2, which 21 is the standard for it. There is another thing, my colleague in UMass in US, he was able to get 23.6, which are pretty okay, because the field has made 27, but still it's not trivial. I have been working with another class of material, which is called the wide-bandgap perovskite. So I was particularly interested in 1.8 bandgap. You can ask why. That bandgap, which has certain composition of bromide and iodide, I can tell you it's 0.6 iodide and 0.4 bromide. And similarly, the cesium MaFa, I have certain composition, which gives me 1.8 bandgap. The interesting thing about that bandgap is it can be used in tandem with silicon.
Oh, okay.
And that's the commercial thing right now, which many companies are aiming at. So eventually,
you can combine perovskite with silicon. You don't have to combine perovskite with perovskite.
That can also be done. But perovskite can also be done. So
this is
instead
more
of fighting against it,
right?
So that's the thing. So this is also a very interesting problem. to how to optimize this 1.8 thing well. But then there are certain, it sounds so fascinating. So for this material, for 1.8 band gap, because we sacrificed on the current part, because we are increasing the band gap, we gained voltage a little bit. The world record is around 20 and 21. Like when I was in the US, I was able to get 18.5, and I have some experiment planned up. It can change. So it's like it's pretty close to the standard. But then again, there are certain problems. There is this thing called phase segregation.
What's that?
Okay, it's a degradation thing. It's like when I have more bromide and iodide, they have certain kind of competition. When they are exposed to light, they tends to separate out. So one will go towards the light and others will move away from light. In fact, there is one study from the group where I was in at UMass. So my colleagues there, they have shown that how this iodide and bromide moves and how to suppress that phase segregation. Because an interesting thing is, it's just like a elastic band. If I keep my device back in dark,
They'll come back.
it will come back.
Wow,
So there is a limit. So you see how many physical phenomena are
My
happening.
God.
But that's a challenge. We cannot have it. Like if I suppose I told you, Clinton, I have a 19% cell, which is wide band gap. You go and put in your silicon, you will get 28%. But you come back, what is this? I'm characterizing, I'm just getting 14%. I kept on characterizing, it became 9%. Then I'll say, okay, you keep in the dark. And next day again, it will give 15%. You'll say, what to trust? What are these values?
Reliability is
Yes.
there.
So initially, the first instinct is just, okay, maybe that's where the academic thing and real things comes up. Maybe somebody says, yeah, I got 15. I'll characterize all devices. I made 40. In all of them, I got 15, my first measurement. But it requires another thing. You observe it, like how they are getting evolved. So ideally, it should stay at the same number.
Right.
So, but then people study that there is this problem of phase segregation. So now this is one of the challenge. Otherwise, it's all set. We have this layer. It works. There are certain methods. Though we have possibility of adding things, but it can result new kind of problem. Like few solution, but few problem.
Right.
So then there are so many
when you
parameters.
solve for one, you unlock 5 new problems.
Yeah. So these are the real challenges before actual commercialization. But still, I'm pretty confident people have worked. And I've seen, like, I was in Boston. So there is this conference called Materials Research Society. So it happens twice. One is in fall, one is in spring. So annually it happens in Boston every fall. So I had this opportunity to listen from one of the MIT's professors. So how they are trying to solve this problem of reproducibility. So you know what is one of the suggested approaches?
Standardizing the lab.
Yeah, but how?
How? Same equipment, same brand equipment or something like that.
Yeah, that's correct.
Same conditions in the lab.
And
moisture.
how to maintain those things.
Sharing the data like IoT from one lab, and it would go for one common body.
So it's like automation. You make everything automated. Like so that's one way. So it's like a future of the field now, like a future of the research if somebody has to continue this field at some point. But wait, till this point we have just talked about the methods which are being used in the lab.
Right.
But we cannot just rely on spin coating on an industry level.
Production.
So then there are other processes. There are certain processes which are more compatible with industry. You know how newspapers are getting printed, or any wrapper, say Lays or other things. So there is this roll-to-roll coating. One thing about this technology is, since this is an ink, so we can employ those things.
Printing process to manufacture perovskite.
So these solar cells are also called printed solar cell at times because they can be printed on a flexible substrate.
Nice.
Okay, so and again it gets so cheap, you see. So if you want to do a commercial production, probably
printing is the way to go.
Printing is the way to go, not spin coating.
Right.
But it does help to study them.
Right.
Here. So then there are certain printing methods. So one of the common printing methods is slot die coating. And again, after my master's, this was the thing I was working at. Not with the perovskite, but with organics, but the concepts remain the same. So now how to optimize parameters of that slot die coater? It's like their dispense rate, from what height the ink is coming from, how fast the dye is moving. Dye is like a sharp head with two ends, and then the ink comes from between, and then it coat as it moves.
Wow.
And so we can have
Even
this
we
as
should
a
give credits to these people as well who design these
yes,
processes, spin coating, dye coating.
exactly.
Amazing, right? Like
And
it's
it's good that we have jumped into the industrial aspect as well. So that's the industry. And many people have been working on it. In fact, different people have their own way of doing it. Like there are people who just want to do deposition. Say, if I can name a company, like there are multiple, but one stands out is the Heliatech in Germany.
Okay.
So they have pioneered this thermal deposition thing. And actually it's a neat and clean, but you'll have to go to a vacuum and other thing. So that's one way. Then again, the combination of these layers, spin coating and other thing, that's the other way. Replace spin coating with something like slot die coating for large scale production, and then probably have deposition things and other stuff. So roll to roll is just like the conveyor belt and the industrial process, one
Nice.
step at a time, and then we get meters of solar cell. So the thing is, with some half a liter of ink, active material, we can paint a football ground.
right.
So that's the bulk production that can be achieved. So in that front, it's not a major problem. The major problem is again the stability, which I mentioned, which
Right.
people have been working at. There is another problem. Can you
Stability,
spot?
reproducibility.
Okay, I'll give it a hint.
Okay.
There is something related with the toxicity.
Lead.
Exactly.
Lead present in the.
Yes.
But since it is coated, like with the
Yeah,
thing,
but what if
wouldn't be come in contact with the people
so
or
that
ground?
so that's a challenge. So like how to encapsulate it properly if we indeed have to use it. But in fact, there is another very active field, which is replacing lead with tin. But the problem with tin is it's highly unstable.
Right.
Like the basic one with iodide, it doesn't even last for it just lasts for a few minutes, the way the earlier version of perovskites used to work.
Right. But let's one you can make it up to 1,000 hours
Yes,
stability wise.
but people have been studying. Even I have a colleague in our group here in IISc who has dedicated his entire PhD in studying this lead system. And there is another advantage of lead. If we mix lead and tin, we can get 1.3 band gap, like even lower band gap than 1.5. Now, if we combine 1.3 band gap, which is closer to the silicon band gap of
Right.
1.1.
Silicon.
If we take another layer of 1.8, suppose we have optimized no phase segregation, we can make perovskite tandem. That's what people have been making. They have made successfully.
And how much efficiency it can lead up to?
It can go up to 30%. Like I think it has been demonstrated 28, 29%. It's keep changing. Like it's tandem, we have it, we can see it. Now we are combining two active layers. So the top layer will have wider band gap that is used for like current matching, and the voltages adds up. So that's how the efficiency gets improved. But the current remains the current of the lower cell. You see, so that's a trade-off. So that's the optimization, and also we need another layer in between because we cannot put metal in between because it will block the light.
Right.
So it has to be something transparent. Okay, so for tandem we need something called recombination layer. It has to have certain amount of property which
Transparency.
can transparency one, and also that transport facilitator property as well. So typically the common things are some oxide, including ITO. That's when I mentioned that if needed we can sputter ITO at our base.
Right.
There are other processes like atomic layer deposition. If we can take some oxide like tin oxide or zinc oxide, and if we coat it, that acts like a recombination layer, very thin, 10-20 nanometers. But again, it's an optimization. So that's what we need, layers. I'll tell you one thing. So I was mentioning several structures. Just see this. I was surprised to see this thing when it wasn't yet published because it was shown in the same conference in Boston in December. This is the state of the art. This is a multi-junction perovskite solar cell. It has multiple layers, you see.
Wow.
This has one active layer,
Okay.
which is wide band gap, as I mentioned in bromide,
Right.
2.3. Then they have another layer, wide-bandgap, which can be used with silicon one also. But this is all perovskite, by the way. It is 1.8 bandgap. Then there is the standard one, 1.55. And a low bandgap, as I mentioned. So it's basically 4 solar cell combined in one, and then to maintain all the optics, all the electronics, all the material composition.
Pass through till the bottom?
Yes, because these are the transparent recombination layer, SNO2, IZO, nickel oxide, and there are series of recombination layer, hole transport, electron transport.
What would be the efficiency for this state of the art?
This is 34.4%.
Wow. So they can play with any of the layer or add top of it.
I mean, yeah, so it has to be correct, optically correct. It should align. It should be within the physics. You see, it can be, so there is a theoretical limit to it. But how to carry out these processes, because it should be compatible with each other. It's just like students forming pyramid in school. Like the higher
even
it goes,
one layer makes a difference.
Yes.
Right? Every layer has to be compatible, stable, non-reactive. My God, okay.
But given the fact that this can be done itself is very exciting.
Right. It's a big achievement.
This is the state of the art. This is 2025.
Wow, okay.
And this is from the same group, by the way.
Oh, who did this? German-based?
No. This is like Professor Snaith's group in Oxford, who have Oxford PV. And then there are other people like that, like groups in Northwestern who discovered SAM material, like a transport material which just changed things in last 2-3 years. In fact, people were moving to NIP structure, but now the PIN is the industry standard thing. So yes, so this is what can be done with perovskite. So we started our discussion with just one layer, but you see the possibility. There is this absorption spectrum, like how much light these active layers can gather. I mean, so it's how much spectrum they are getting.
Right.
So it's the optics, electronics, photonics, everything should align. And the magician, the chemist who designed these molecules and come up with this.
How stable was this state of the art?
I mean, I don't know. Like, I think it was mentioned for stability. Also, there are certain protocols, like how it should be studied, because different people can have their own approaches. So now the field is moving to standardize a few things. If we have to study effect of temperature, then say it has to be studied at, say, 85 degrees centigrade continuously. If it's under light, it should be under same amount of intensity, same amount of light spectrum. If it's at humidity, it should be at the same humidity. So basically these 3 are the parameters. Then the ambient condition, whether it's in nitrogen or it's in ambient. So again, if you remember the glove box that we will see, so that's the control environment to carry out the processing, and then the other thing.
Okay. So we went from 3.8% efficiency in 2009 to over like 33% in just 15 years.
Yes.
That's incredible. Like silicon took decades to achieve those kind of efficiencies. The breakthrough happened in 2012 that showed perovskite has a huge potential. Then it was a series of aha moments everywhere. People trying to figure out layers, tandems, each materials. I mean, so many variations.
Yes, and cumulative efforts of so many
people, right?
Yeah. Though few people pioneered, but then others have capitalized and...
Right. So let's see. I have few questions. I've got the broad idea of perovskite.
Sure.
How it's different.
Yes.
So like silicon is stuck at 26% because of physics. Perovskite could theoretically go much higher by using multiple layers. That is the summarization. That's like comparing a single-story house to a potential skyscraper.
Yeah.
So what is the theoretical limit of efficiency for perovskite in tandem? Like how far it can go? Beyond that, it's impossible to go even for a perovskite.
Okay, that's a very important question, because after some point we cannot just keep on adding the layers,
right.
Because it will disrupt the whole thing. So I think the 4-junction thing, I think this has to be the limit. So theoretically, I'll have to see the exact calculation, but it should be around, I think, 40% for this structure, 40 or 42. And so if we could push it to 37, 38, practically, it will be a good thing.
So that is almost double of what silicon can do.
Yes. Efficiency is not a problem, I would say.
Right.
See, even the this one is like silicon one, 15% we were able to commercialize.
Right. Now, okay, let's come to the manufacturing cost of perovskite.
Wow, nice.
So,
I am ready with that.
okay, so perovskite manufacturing looks very simple. As you said, printing. It's
simple but not trivial.
You don't need a high temperature for, perovskite, right? 100 to 150 degrees Celsius. So does that mean lower cost of manufacturing perovskite?
Absolutely. That makes a hell
Even
lot
the
of difference.
sophistication of the equipment required. How much can you think of cost drop in manufacturing the perovskite compared to silicon?
Okay.
How many folds? Like silicon, if it cost 100 rupees for silicon, what would it cost for the perovskite?
So that's very important question. Even before starting the research, it's advisable to have that calculation. Even once we were discussing among ourselves. So I searched it. So here is the precise answer.
Interesting.
Not only with the silicon, but the other technologies as well. Basically perovskite, silicon, tandem, and also organic I have added. So if you see the cost comparison and this technology, blue one is the silicon, orange one is the perovskite, green is the organic, and this is silicon perovskite tandem. So if you see the cost of these material cost, it's lowest. Perovskite in lowest in all of them. Processing cost, you see silicon. So silicon perovskite is still costly, but it is less costly than this one. So precisely this is the answer for this. But as you can see, it's much lesser. There is one more thing, something called energy payback time. Suppose if silicon is 25 years and perovskite is only say few months or few years. So what if everything is all good, but it's so low that when we can recover, like whatever, yes. So there is this thing there is this calculation for that. So the term is called the energy payback time. So for crystalline silicon, if it's 1.5 to 2 years, so of course there are certain assumptions because some of them can take 8 or 9 years because the things go bad. And that we have seen even in India. Even our professor teaches one course where we were told that
because sunshine doesn't shine all the time.
It's not only that.
It's rain.
It's the way it is maintained. If it is cleaned in a certain way, it can develop some cracks over the top layer and the efficiency will go down. If there is a tree shedding, it will go down. If there is dust, it goes down. And also bird droppings, the other things, it goes down. That we don't consider while doing research, but that's the actual thing. But let's say ideal condition, if it is 2 years for silicon and in India is around like rooftop is around 0.44 years, then perovskite is just 2-3 months. So it's much lesser.
The only thing is the stability is the only problem.
Yeah, but even with so like it has to last for that long. So that's okay. If it's not lasting for 25 years, if it lasts for 3-4 years, given the processing is easier, we got the payback time, and we can
buy it again.
Yeah, we can have multiple sheets and then install it.
Right.
And there is one more application like you mentioned metal.
So as you said, you can buy it like a reusable aluminium foil. Use and throw.
Yes.
Right, and that's
of course
why
it should be discarded properly because it has lead.
That's why toxicity is the problem.
Yes.
Because it's use and throw. It's not lifelong.
But
disposing
our approach should be to make it lifelong. But
right.
Even if that's not that much long, like silicon, still it can be worked around.
Why silicon is so thick and this is so film,
That's very important question. Actually, it's scientifically also it's a very important question. This is because of that very thing that I have mentioned a few times. It's called absorption coefficient of that material. Like how much light is getting absorbed. Like what is the thickness of that layer which is required to absorb all the incident light. So for silicon, it's few micrometers. For perovskite, it's just 300 to 400 nanometers. If that thickness is less than that, so there is this term like it's 10 to the power 5, so that unit. So some material will have 10 to the power 2. That means their thickness should be higher. I'm just giving examples. So that plays a role.
Okay.
We cannot make it very thick because then the charge collection will be a problem because the charges will have to travel that distance.
That means electrons and holes recombine before it reach the plate.
Yes, exactly.
Okay,
Exactly.
okay.
You understood it well. Yeah.
That's why you make it thin.
Exactly.
And
Precisely, that's the reason.
Don't lose electrons.
So we cannot make it very thin, otherwise we won't be able to utilize all the photons. So that will reduce the efficiency. At the same time,
You can make it thin and tandem.
yes, that can be done. That's how we have different layers and other things.
Right.
But that's a different kind of engineering.
Engineering.
So again, one
Okay.
of the infinite
Multi-junction
possibilities.
needs device engineering
Yeah.
experts. Okay, amazing. So we have got higher efficiency potential in perovskite and lower manufacturing cost, and it is already started to sound too good to be true. So the catch is stability, reproducibility, and toxicity.
Exactly.
Okay. Is there any other problem?
Practical issues, as I mentioned, there could be. Once it is deployed, we'll come to know.
Silicon is like a brick wall. Perovskite is like origami. You can fold it.
Yes.
Like you can.
We can print them like a newspaper.
Yeah,
We can have
newspaper.
bifacial or semi-transparent solar cell.
Right. And you can use it like a window blinder.
Yes.
You can use it as a solar windows. Solar panels that could be integrated into clothing, curved surfaces. You can like have a perovskite in your back, colored perovskite in your jacket, which is connected to the circuit, and you can charge your phone.
Yes.
That can be done. Cool fashion brand it would be. And that opens up to so many possibilities instead of just like putting solar panels on roof. I like the color tuning aspect.
Yeah.
So we can adjust color of the perovskite. Where do you see perovskite in next 10, 20 years?
It has started. I believe some version of perovskite with less toxicity or with better encapsulation and with some steady reproducibility. If that comes, say with automation or other things, then definitely there is a future. Even for perovskite single junction, because it's very cost
Do you
effective.
see it replacing solar?
Definitely,
I mean, silicon?
no, I don't think so. It will replace. It will complement. It will have its other niche of application.
As a tandem silicon.
Tandem for rooftop, but as I mentioned, like there are things that cannot be done with silicon, like integrating with clothing and other things, building integrated.
Right.
So it will have its own application.
Application.
But it won't replace because other people have also not stopped working.
Are there in commercial tandem silicon?
They are coming up very soon. So
soon.
In fact,
which
like,
company is rolling it?
Okay, so there is this collaboration between Oxford PV and a Chinese company, like they're the giants. So they have combined.
And what is the expected efficiency they are promising to the
I think
market?
efficiency will be around 25%
25%.
for silicon perovskite tandem.
What is the normal efficiency for silicon in the commercial? 22%, right? 20.
I mean, it depends like how crystalline the silicon is. But what we see everything around is 15%. It won't be that much crystalline.
Right.
So like it's a decent number.
25% is a good number then.
Yeah.
Right. You have dedicated your career to this material. When you look at a perovskite solar cell in your lab, what excites you the most about its potential?
Oh, it's a nice question. So what excites me the most is, even during my PhD, the field has moved so much. So the materials or the transport layers I started working with, now it's all changed.
Wow.
So
Even you have started changing the...
even within my PhD time, even the structure PIN to NIP, and I'm still in awe when I see those effects. Like I could read few things in the paper, like this wide-bandgap, this much has been achieved. But when I go to lab, when I perform experiments on my own, I learn everything new. That excites me the most. And there are challenges. And then I meet people who are enthusiastic. And also, I meet people who are skeptical about the field. Both of them are equally important.
Right.
They keep us grounded. So that's what makes it very interesting in terms of research, at least.
You wake up every day, go into your lab to work on something most people have never heard of. But that could change how civilization powers itself in the decades to come. That's pretty wild way to spend your life, honestly. So I want to understand what the journey has been like. So let me explore. How did you first stumble upon perovskite?
I was always interested in science in general.
Okay.
Maybe watching backyard science during our childhood or Discovery and National Geographic. And I was very much interested in astronomy and astrophysics. So that motivated me. So somewhere subconsciously, I was sure that I will pursue higher education and I'll do research. But no, it wasn't just an instant that I want to do materials engineering and other thing. In life, sometimes we are unsure. That happened with me. Though I had a surety that I wanted to do a research, but first I wanted to become an engineer. So I picked electrical engineering, which gave me possibility that I could go anywhere. I can go into IT as well, leaving the core electrical,
Right.
and I can dig deep into the material and physics part. So my research journey started when I joined molecular electronics lab at JNCSR Bangalore, Jawaharlal Nehru Center for Advanced Scientific Research. So I really thank them because they picked me from obscurity, I would say. Professor K.S. Narayan was my supervisor. So at first it was really challenging because it was all new. In fact, the few of the courses that I was taking, I didn't even have the basics because the people were from the basic science background, from the premium institutions of India. I came from a relatively humble backgrounds. Even we never talked about research publication during my undergrad. It was all about the jobs, sitting in placements or applying for government jobs, give gate, PSUs, those kind of atmosphere. So it's strange, when I see the undergrads here at IISc, they have so much of the exposure. So when I look back, coming back from there, so it all started when I joined masters. Then I thought, oh my God, people take research source, papers, publication, and this is what the research is. So I had a great training there. I struggled. I stumbled in few of the courseworks, the few of them, but that's where I learned the most. While spending time in the lab, seeing my colleagues, so I was in an molecular electronics lab where people were working on the devices. So I got to learn about these things, the same field effect transistors or solar cells. Then some of my colleagues were working on organic solar cell. And during that time, I was fortunate enough, that lab, that time there was this Indo-UK collaboration kind of thing. So I was fortunate to be the part of that research. That's when I got actual perovskite solar cells. So one thing was sure that I wanted to work on the solar cell. So I fixated on that.
Okay.
And it turned out that the perovskite was a thing coming up. Okay. It was 2016 and 17. And I was from an electrical engineering background. So my first problem was how to characterize them, to know more about to gather more insights in the fundamental charge transport phenomena and the degradation mechanism. Professor suggested me a very interesting problem, and even till now, that is my favorite research problem. Considering I was just a master's student, though it was master's by research and it had similar protocols as a PhD, it was a mini PhD. So I learned a lot during that process, and it was really a challenging problem where we worked around a technique. And very few people, even now, not only in India, I think India, that lab has that's the only lab which has that technique. It's called noise spectroscopy. Even in world, there are very few people who can characterize that thing. In fact, I was the first one to characterize using that thing. I means we were the first one as a group. And still that technique is not utilized to its potential. So I learned that a lot. So after that, I was sure it's really interesting. This the third generation entire thing. So then talking about academia and industry are different. So after completing my master's, I got a chance to work at the National Center of Flexible Electronics at IIT Kanpur, where I could bridge, where the theme was to work between industry and academia, that how to take from lab to the industry scale. Till that point, I did not make solar cells on my own, but that's where I learned the solar cell. And the interesting part is I just started directly with the industry processing thing. So I was working with slot die coating, taking this thing to that. But then for my PhD problem, I came back to perovskite. They are all these sister technologies. So there it is during my PhD, which started in October 2020, the COVID time. And this is also slightly funny. The first year I was at my home just taking courses and doing stuff. And the last 1 year I was again away. So I got to learn like at different instances. And now I have myself made like some of these combinations.
Wow.
Especially one of the things that I feel happy about, that I work with different band gaps material, which have direct inclination in tandem and multi-junction, as we have talked about. So yeah, I have made my effort to just make some dent.
What does a typical day in your lab actually look like? Walk me through it. It's not like every day, oh, nice, holy shit, those moments. So
It's like doing the same thing and expecting the different results. So there are days like when we are highly motivated, we want to complete our experiment, but there are days like they just pass. So, but I think those also play a very important role when we sit back and think, because sometimes we cannot do it as a machine because it's not like a factory production task. So sometimes we take back for days, we realize, okay, let's come back and observe the same result with some different angle. So if you ask us, it's something like filmmaking. The research is like filmmaking. Like you have pre-production, that you plan certain thing. So our experiment is forming one hypothesis. Then in lab, we go out and test our hypothesis. Like what we thought based on our scientific understanding. Say we had some simulations and some result like this particular combination should perform like this. Now the production is the actual experiment. But then the toughest part, the analysis, which is the post-production. So that's our typical day. But yes, it's not like a perfect day. Everybody's have their highest motivation. But the thing is sticking with the problem and being human, people do feel all sorts of emotions. Sometimes people get frustrated and it's not entirely their fault. It's about that reproducibility of the material. But if you ask me, I like it. I don't mind getting different sorts of result because I'm just an observer. And how rationally I can observe by standing off the shore, that's what counts me the most. So I am here for the process. So that's my mindset, but others are not wrong in feeling what they are feeling.
So here's something I'm really curious about. Like, what's been your most beautiful failure? The time when something went wrong, but actually led you to something interesting.
Oh, that's a very nice question. So we had this collaboration in one of our groups, Professor Rajiv Ranjan, who is currently the head of our department. So, by the way, that problem is still not yet solved completely. But our idea was to mix perovskite with some other materials, like ferroelectric materials. So
magnetic.
Yes. So again, there also it's a perovskite material. So in fact, they are masters of those material. So and they have published some really good papers, including Nature. So I got a chance to work with that kind of material. So the hypothesis was that those piezo ceramic material are optically sensitive. So what if we combine with the solar cell? It might lead to the enhancement in the performance. So we conducted some preliminary experiment. We did not directly add it into the bulk of the material since our material is solution, so which gives us freedom to try out new things. So what happened? We introduced this material in one of the transport layers. So very interesting thing happened. We were expecting to see some improvement or not so improvement in the perovskite solar cell. I mean, we are putting something, either it won't work. That's very common thing. Like it did not work as solar cell at all if we are putting something. But interestingly, it worked as it has some memory device, which is sensitive to light. So depending upon how long the light is exposed, it started to shift its characteristic. And it had a similar kind of characteristic. That's what we see in memory devices, set, reset. So while we were looking for a solar cell or improvement in solar cell, we were seeing an entirely different mechanism, which we are still trying to solve. But it's a beautiful thing. Like we expect something, but nature doesn't work. Yes. But it's entirely it's a fairly new phenomena, I would say. which we are still trying to figure out. So it wasn't a solar cell characteristic, but how that material interact with the new material, or like when that material is put in this kind of scenario, how it is evolving, how it is changing. So that's a very interesting thing.
So you mean when you exposed it to light, it started behaving differently?
Differently. Like when that piezo ceramic materials is introduced in this...
Piezo means vibration sensitive,
No,
right?
piezo is basically, with definition of piezo, are something which change in their configuration, like strain or thing. Mechanical change leads to the electricity. Then there are certain class. So there are ferroelectric materials, which are subset of this piezo materials. So like they can be polarized. I mean, it's entirely different material with different jargons. Even I'm not an expert of that.
Right.
But when we mix two things and we are seeing something, so the thing is, can we control that trend?
Nice. It's like a jazz musician who say best performances happen when somebody presses a wrong note and everybody else follows on that note,
and then
something
improvise.
that never planned, right?
Yes.
What strikes me about researchers is that like you're working on timelines that are longer than most people's career on problems that might not pay for decades, right? That takes particular kind of faith in the future, right?
Yes.
Like, even if you're working on it problem now, even if it's successful, it may take 20 years or 10 years or 20 years to really pay off. That is really being an optimistic, like, that requires certain faith in the future. So that's the beauty of research again. I mean, the Japanese researchers, as you said, he done it in 2009, and now things are still evolving, and
Yeah, but at the same time, somebody has to do it. Not everybody needs to do it,
right?
But somebody has done it. That's why we are not living in caves.
Right.
Maybe people can debate, like, it's okay, what's wrong in living in caves also, but in terms of development, because somebody had strived, and then humans, they collectively came together, and then we could, yes.
Okay, so now let's talk about global race. Let's zoom out and look at the big picture. There's a global race happening right now to crack the perovskite code and bring it to market. So Apoorva, from your experience, from your perspective inside the research community, who is leading this race and why?
I think UK and China, they are leading the race.
Okay.
Firstly, like UK, because like they had this advantage because this thing was discovered there.
Oxford PV.
Yes.
Because of Oxford PV.
Yes. But other people are also not far behind. In fact, I've seen people are working closely together in collaboration as well. I don't precisely know the policies and I cannot comment on it, but like, in fact, there is one collaboration between a Chinese company and the UK company. And then there is several good works, some companies like Tandem PV, First Solar in US as well. What I've seen, the community is pretty close. So people, they do meet each other on a regular basis and share knowledge, at least up to some extent. But definitely there could be some internal policies of national interest. So, I mean, that's always there. Yes.
Right.
That as a scientist, we may not be fully aware of, but it becomes very important.
So you mentioned UK and China. So what's interesting is that this isn't just about having smart scientists. So it's about having the ecosystem to support this kind of research. What does it take to be competitive in perovskite research? Is it just smart scientists?
I think in terms of smartness, Indians are no second to any other. Even in all those major labs, you will definitely find few Indians in all the major labs.
Right.
So that's pretty much the same. But in terms of, it's more of the intent, and few people are working towards it, but the more people should work. So first the intent should come. So many times, like especially at the student level, people tend to play safe, which is understandable because there are few tasks at hand. Like you finish this milestone, then you do that. Even amongst peer, it might get discouraged subconsciously to why you even think you are talking about those things. Like who you are to even think about those things, and especially with so much uncertainty.
Right.
So maybe that intent and mindset change, then probably the other policies and those things. I think, but there is improvement.
It's
but
like
I can
a
sense. But
Formula One racing. You need a great driver, but you also need a best car, best pit crew, best technology,
exactly,
and deep pockets.
deep pockets, yes, and everything should synchronize.
Yeah,
Work in
no
synergy.
single element is enough.
Yes.
Yeah. I'm kind of curious about the dynamics here. Are researchers sharing knowledge across borders, or is this more like a secretive arms race? How collaborative versus competitive is this field? Would you say more competitive or more collaborative is this field?
At least so far, I would say it has been more collaborative. As you see, even the first paper, like it could reach 12% because people collaborated. I myself have been part of some of the major collaboration, and I have not yet finished my PhD. So right through my masters, I had collaboration. Then I went to France for some characterization collaboration. I went to US. It was again a collaboration, and I see people meeting, and their research are out, and scientifically we can question them, and one has to answer like scientific queries. So I feel it's still a collaboration, at least in terms of lab research. It's highly collaborative. That's how the field has moved so fast. It wouldn't have been possible with only few people or one country doing that. But in terms of deployment and other things,
Commercial
that we'll have to see.
Right. So it's simultaneously most collaborative and most competitive field together simultaneously.
Yes. It's competitive because every day new discovery is coming up.
Like scientists are sharing fundamental insight while also racing to be the first to market with commercial applications.
Exactly.
Okay. Let me ask you about something specific, Oxford PV. You have somewhat association with them, with the founder of the Oxford PV at some point in time.
Yeah, I worked with on one of the projects, my master project, where we used to get perovskite solar cell from their lab.
Okay.
Because that time they were the one who could make reasonably well performing solar cell, because it was still new. And we wrote a paper together.
So Oxford PV seems to come up in a lot of perovskite discussions across the world. I mean, wherever you go, Oxford PV comes first. So what makes them special? And are they as far ahead as they seem from the outside? Are they still ahead?
I think they will be ahead because they started early and they had all right kind of people. They had made some of the important discoveries. So they had a head start so that they retained. Of course, they capitalized on it. They worked around. But others are also catching up, I would say.
Okay, let me understand India's position here. So we have incredible technical talent, world-class institutions like IITs, Indian Institute of Science, and a desperate need for clean energy solutions. So where does India stand in this global perovskite race?
Again, there are so many people like who have worked with those like major groups and other thing, and many have decided to come back. So they are making efforts. So I hope in next 5, 8 to 10 years, we will see substantial changes. And if not par, we will be comparable to the rest of the world.
Nice.
Yeah.
If a brilliant young student in India today said, I want to work on perovskite research and make a global impact, what would you tell them? Should they stay in India, go abroad, or does it depend?
I would suggest them, they should not rush. They should first explore like what the research is like. When I went to my first lab, so we may have certain impression from outside, but everybody is different. Their choices are different, and our priorities might get changed over the time. Correct. So it's important to stay flexible. But once you decide, just go all out, whatever you want to do. At least finish that chunk.
Right.
Do not get demotivated. It's fine. Like, be careful what you wish for first.
Okay. That's nice. Okay, let's close to the final interesting chapter, which I call Startup Thought Experiment.
Oh, nice.
Okay. So imagine I walk into your lab tomorrow with a briefcase full of money and say we are starting a company. I'll be a CEO, you will be the chief scientist, and we are going to make perovskite solar mainstream.
Okay.
We have smart investors who believe in us, and we have 5 years to build something that matters. Money is not a problem, not a big problem.
Okay.
So what do you say? Are you in?
That's a nice question.
Okay.
one word answer, yes.
Okay.
But I'll add few more assumptions.
Okay.
Assuming that all those problems have been solved,
Which are those? Stability?
reproducibility, stability,
Okay.
and other phase aggregation. So we know that we have a pilot project. It works. It works every time. And all other challenges are resolved. If that's the case, why not? Yes, all out.
Awesome.
That's what I would like to do.
Where do we even begin there?
Okay. To begin with, we should acknowledge, like, we should have thorough understanding of the what space we are entering. So we should start with the comparison with the other technology in terms of cost cost estimation.
I like the way you made a presentation.
Yes. So, like, if you see the estimated cost for manufacturing is around like 80 to 150. Like, it's about the production, like how much power we are generating. Like, if it's in megawatt, so like the cost per watt for silicon is around 0.4. And for just perovskite single junction, it's half. So we have head on it. And if we are going to make perovskite silicon tandem, then the cost is not less, but we can produce slightly higher output, like 80, like around 170 upside. So we will need money. So that's one thing we'll have to keep in mind. And also, if we really look into the revenues, we'll have to see the markets, like who are our buyers.
Right.
So probably we'll have to look for that very seriously. In terms of technology, that's fine. Like pilot project, it's fine.
On the market.
But those are the things. So we should first see this, like where we stand, where we are heading towards, what are our competitive products. And then suppose there are few things like how much capital will be needed and what is needed. So we need like basically three things. First is like our R&D, our lab space.
How much it would cost to set up R&D?
Okay, so that depends upon what scale we want to go. So again, those will be
go with the pilot scale, small scale, where we can prove we have a badass MVP.
Yes.
So that's all. We're not risking all the money.
Okay.
So we'll take the minimum money, take the big risk with that money.
So there are two ways of doing it. One, like, since you mentioned the money is not a problem, so I'll go with the first way, that I'll set up my own lab. We'll get those equipment.
Yes.
Like lab standard
equipments.
like thermal deposition, glove box. I would rather like to make it automated so that we have reproducibility.
Right.
And
robotic.
And get everything set up and start making it and have slot die coating and like roll to roll compatible thing.
Approximation number in terms of rupees, crores, dollars.
So as per this basic calculation, it's between 0.5 to 3 crores.
3 crores.
Depends upon what.
Per year or setup cost?
It's setup cost.
Okay, and maintain that
and then,
year.
But maintenance will be again,
considering it is running continuously every day.
At least 30 lakhs.
30 lakhs every year.
Every year, 30 to 50 lakhs.
So
basic.
say 4 CR on R&D.
Yes.
Okay.
And then getting into the pilot stage itself will be between some...
Pilot stage is what is required, like producing materials.
Like we have a product ready to demonstrate.
Right.
And then it can be improvised further as per the market requirement. So it's a crude calculation, but still I would say like between 20 to 200 crores.
200 crores.
That's the upper limit.
20 to 200 crores. Yeah. Okay.
And again, since money is not a problem, if money is a problem, I'll answer it differently.
Okay.
Yeah.
Okay, money is the problem.
There are already labs in academia, like who are in that stage.
Okay.
So probably it's better to collaborate with them, work together. That will be faster. Like so that's the way to go around.
So what happens in the pilot stage? Like why is the cost 200 CR?
Because I mean, you have done all the research and now you have made these optimized thing. So that optimization and everything else and testing itself, because it's not only the manufacturing, but to test them and with encapsulation and other things. So that will cost. Also, it will require human resources, skilled people to do it. We may have to certify and do some tested somewhere outside to get the better credibility and other things, because that's also important because it's a global field.
Let's say it's about 25 CR then. We'll keep it to the minimum.
Yes, yes.
25 CR.
Yes.
Okay, then another thing is full
Full
scale.
commercialization. Then
That is comes in manufacturing,
Yeah,
right?
manufacturing,
So
yes.
until we do our MEP, this is enough.
Yes.
Pilot and R&D.
Yes.
Until we prove a material which is stable and people are ready to pay and
and it's safe. Yeah.
and ROI is faster
Yes.
compared to silicon. So we need to build a minimum viable product here. So that proves perovskite can work in the real world. So what would be the best MVP? Like what product can we make?
Okay, that's
go with
interesting.
the
I'll
tandem
go with the
only?
tandem first,
Mm-hmm.
but I also see future in flexible electronics and semi-transparent or bifacial solar cell, like different colors, like power generating windows, those kind of stuff. I think there is a huge potential in that. In fact, that is one of my favorite products if it ever comes.
Tandem is a way to go.
Tandem is a way to go.
Yes, all silicon tandem or perovskite tandems.
If layers are optimized, then why not perovskite tandem? Because the
Right.
cost will reduce because it's all
Amazing.
perovskite.
Even if we reach 25% or to 30%.
We already have reached 27, 29% with perovskite tandem.
Okay.
It's just working around the other aspects.
Nice. Stability.
Stability and
reproducibility.
yeah.
Okay, with the lead based or without lead?
With lead.
With lead, right.
With lead.
Okay. I think we need a stronger encapsulation.
Yes.
We need material scientists, device engineers, manufacturing experts for this, right?
Yeah.
And that's an expensive talent.
Yes. Chemists.
Chemists. And who else? Anybody else in the scientific team? Who do you want in your scientific team? What would be the roles? Like one is, as we discussed, material scientists,
Yes.
chemists, device engineers, manufacturing experts.
Also, somebody who has understanding of the market, how market works, how revenue gets generated.
That's
So-
fine. That's business aspect.
That's a business
Just in
aspect.
the
Okay,
science,
scientific aspect.
Yeah.
Somebody who can work with all of them, who can glue each other, like who doesn't understand 100% of everything, but understands 80-85% of all the aspects.
Okay, that can be you.
That is needed.
Right. You are that. You are this chief scientist here.
Yeah.
So you have to hire those people. It's about type of minds as well. Like it's not just about skill. It's a type of minds we also needed. So what kind of personalities and thinking styles do we need in this team?
Somebody who stays with problem for a longer time, like being patient, but at the same time innovative enough to just not getting stuck on a thing. Just try out new ways to overcome the problem.
Nice.
Like one
Think
who acknowledges the problem and also try to solve it.
Nice.
Who takes pleasure in solving the problem.
We also need people who can think big and small
Yes.
and who can dream about changing the world, but also obsess over why something degraded 2% faster than expected.
Yes.
So we got 30 CR investment to set up our R&D and pilot programs. So we have taken the money. Now, as a CEO, I will be lying awake at night, worried about what could kill this company. Okay, so what's our biggest technical risk and how do we plan around it?
So again comes down to that stability and other aspects. Like once they are deployed, are we delivering what we promised? Say we said that it will work for 5 years, it should work for 5 years within those like extremities that we mentioned.
Right.
If it fails,
Moisture,
if
rain,
it fails,
water.
just like we have seen these examples in some of the automobiles and other things, like they came in the market with huge expectation, then we see some products getting burned or something.
Right,
So
scooters,
those
right.
will be the challenge.
So how can we minimize that challenge? Plan around it.
That's where the pilot cost goes high. So that's where we need more investment and more
R&D
things. Yes.
more testing.
Yes. So if we want to save time, we'll have to increase money. Do
on
things in
pilot
parallel.
things, right.
Yes.
Good point.
It will save on that like production line 1,000 crore. Like, so it's better to invest 20 crore more here.
Right. I think we could partner up with governments
Yes.
of Indian, like state governments, and installing, like Karnataka is northern dry belt, lot of sunlight. No, like solar farms can be like tandem perovskite farms, and where government is investing money, and we can partner like private-public partnership.
Yeah.
Like if we win, government also wins, because
Yes.
this is the future, and we will gain the advantage on manufacturing these tandem cells. Like we can, like, if we win, government also wins. So let government partner with this in terms of buying our tandem cells and installing it. That also helps us give better data. And
That
in
could
terms
be
of
a way to
testing,
go.
way to go,
If
right?
other like policies and other things are aligned, that's a reasonable way to
we can
move
lobby the
forward.
government. So if we solve the pilot, we got the wonderful stable material, perovskite, tandem perovskite, which is stable enough for 3 years. With the ROI in months, like 5 months, the customer would get the ROI.
Yes.
So whatever money that customer has spent on tandem cell would get in 5 months, but the life of the tandem cell is 3 years. Okay, so we got that stability. We cracked 3 years of stability with that tandem cell with 25% efficiency, or 25 to 30% efficiency. Now, question is, what about manufacturing? How do we take from pilot to manufacturing?
I would say is pretty much doable, because that's the advantage of this technology. We do
Okay.
not need those big
machines.
big machines or clean rooms and other things. We just need this roll to roll, or like flexography, those kind of like printing technology. So that I don't see as a bottleneck. That's pretty much taken, because lots of research has been done.
Right.
And in fact, in terms of pilot production, that's the key, to take from lab to this. And that's doable based on my personal experience also. It's not trivial again, but it's doable.
So with the 50 CR, we cracked the pilot, and
Yes.
then we proved the product. Then we can raise money for manufacturing again,
Yes.
another round,
Yes.
to take this pilot product to the large
To
scale
the large
production.
scale production. Yes.
Crazy, great.
That's doable.
Yes.
I'm positive about it.
Positive about it. Okay,
Yes.
so you would say 50 CR is a bare minimum investment for a company like this.
If
it should
we
be
want to go really long run, and we
Long
are
run
serious
and-
about it.
Right, and not being dead
Yes.
for a short time.
Yes.
Right. So 200 is a safe bet,
Yes.
safe side.
Yes.
I mean, this has been, personally speaking, I've been obsessed about perovskite for
Okay.
a long time. When I heard about perovskite, it was in 2018.
Okay.
When I was preparing quiz questions. So my aim was to introduce new knowledge, new ideas to students for whatever field. So when I was researching about questions to prepare, then I happened to read this material, like which crossed the efficiency somewhere around 25. I don't know. I don't recall the number, but it was a big hyped up article, and which happened to read in Nature.
Yes.
Then it's like, what is this material? Wow. Then so many thoughts. Wow. Delusional thoughts. Then I felt like, I should make money and, invest all that money into, blindly put into this material. I had kind of those kind of, ideas.
I know what you're saying.
Right. Like go all into this material, because I see this is energy problem. So one who solves energy is the thing. I mean,
Yeah.
I'm pretty interested. Like down the line, if I can raise 200 CR for this, you in?
Yeah. Awesome. Yeah.
Okay.
Nice.
Okay. So 50 CR is also okay.
Yeah,
but
that's
you're saying
doable.
suggesting not to. I mean, minimum
Yeah,
is
and
50.
there are people we can collaborate
Right.
with, and like those
Okay.
who have basic level of understanding.
It would take me a long time to do this, but yeah.
Maybe by that time the other problems will be
Problems are
solved.
solved. Okay.
And we'll
Nice.
get a broader picture,
Broader
a clearer picture.
Right.
At least with our discussion,
Right.
we came to know like what are the different aspects.
Right.
And clearly there is a thing like what has been shown and what really is experienced. But it's still, the technology itself is really promising. Something
New
which
knowledge
was not
is
heard.
developed. New knowledge is created, discovered every day.
Yes.
And yeah. By the time I raise money, I think we have solved a couple of important problems.
Yes.
Okay. Hopefully.
Probably would have combined with some other
Materials. Right. Thank you so much. It was fantastic talking to you.
It was my pleasure,
I-
and thank you so much for coming all the way here
Right.
on campus
No,
and just
I learned a lot.
same here. I mean,
It's like last time I touched electronics was way back in my, it was around 15 years ago. I think kind of fresh back, like NP, PNP, bandwidth. It's quite nice. So I want to see your lab before I close this.
Sure. We'll
I
go.
want to take a tour about your lab.
Yes.
And also see what you do. And let's get to your lab.
Sure. We'll go there.
Yes, let's go. It's already 2 a.m. in the morning and IISc doesn't sleep.
Yes.
And we are just outside Apoorva's lab, Materials Engineering. Can we get the tour inside?
The group is called Organic Nanoelectronics Group, which is headed by Professor Praveen C. Ramamurthy. Let's get in.
Okay.
So this is the lab. So there are few major sections. On the right hand side we have chemical synthesis area. Maybe we'll just quickly walk through it. So as we talked about different materials, so some of the materials can be synthesized by the chemist.
Here?
So,
wow. This is
different
your
places, like
perovskite synthesizer?
not specifically perovskite, because people do work on different aspects. One of the major research areas is sensor which can detect contaminants in water.
Okay.
So, but including the perovskite materials. So people synthesize material
Multi-purpose lab it is.
Yes.
So have you worked here to synthesize?
No. I'm not an expert in
As a
synthesis chemist. I'm a device engineer.
Perovskite synthesis is taken care by the chemists.
Chemist people.
Not you guys.
I'm device engineer. Yeah.
Stacking.
I take material from them and then try to use it.
Okay.
Yeah. By the way, since we are here, so there are certain things like we need to clean our substrates. I mentioned glass and ITO, that's what we get. So there is a procedure, like we use one kind of soap solution, then there is one thing called deionized water, like ultra pure water, and then acetone, IPA.
Sterilize the glass.
Yes,
completely.
yes. And then we also do some other treatment that we'll see inside. And I think we can just go in.
Okay.
Maybe just one thing I would like to show. This is called sonicator.
What? Sonicator.
It's called ultrasonicator.
Okay. What
so
it
it
does?
uses like those specific low frequencies. Like
sound frequencies.
From frequencies to clean it.
Clean the glass.
it. So to create those vibrations that will.
Wow, you can see the vibrations here. So this vibration would take care of the cleaning of the glass.
So the things will get detached with those vibrations. This is the area where we characterize our material. So as I mentioned, like UV visible spectroscopy and photoluminescence spectroscopy, like how well they optically perform. What are the absorption limit within a particular wavelength?
UV light spectroscopy.
Yes, so we have quite a few of these experiments. This is FTIR. So this one is used for understanding how bonds are like bonded together and several other basic fundamental things regarding the synthesized material. And this is the instrument I was talking about. So this is the UV visible spectroscopy. So the principle here is it will measure the amount of light falling onto the material, how much it is getting absorbed and how much it is getting transmitted, so that we can get a spectrum. So using this, we could calculate that firstly the absorption itself and the band gap that I mentioned from 1.3 to 2.3.
From that we can extrapolate the efficiency.
Yes. This is photoluminescence spectrum. Again, a very important technique to know the photophysical properties of our material.
Photophysical properties. What do you mean by that?
Okay, so it's like photo means light. And physical means physical phenomena is happening. So like again, it's based on the principle that a certain amount of light falls on our substrate. Now depending upon that material properties,
reflection, refraction, diffraction.
Yeah, so what happens, the electron goes to the high energy state, when it comes back, it emits certain amount of light. So it captures that light.
Okay.
Depending upon that, all the materials will have their corresponding peaks.
You get to see what light spectrum it has absorbed.
Yes, so
Okay.
it gives information about the certain kind of properties, like physics aspect of the material, like what are the phenomena happening to it. So it helps our characterization.
Okay.
This here is a very important thing. Throughout I was mentioning about the thicknesses, 50 nanometer, 100 nanometer, 450 nanometer.
Right,
How
right.
do we even know this? So this is a method. This is profilometer.
Okay.
So we keep substrate here, and then it can measure precisely.
Wow. How much such thing would cost?
They cost a lot. So like 25 lakhs. It can go from 25 to 70 lakhs.
Oh my God.
So
This one?
similarly, yeah, same kind of thing.
range. What is this lab?
So we call it clean room.
Okay.
It's not of that class that what we went with the silicon processing.
Okay.
But this is a humidity control room.
Yeah.
So this is our main working area.
Wow. This looks so sophisticated.
So this is where we actually fabricate the device.
Okay.
So I mentioned about the cleaning. Once we have the clean substrate, we do another treatment, which is called UV ozone cleaner.
After glass substrate is cleaned,
Yes, so
the glass
even
is subjected
there
to-
can be some oxidized impurities still left because in ambient there is enough oxygen. So this has one process, ozonization process, that it removes away any residual oxidation impurities. In nutshell,
That means glass substrate is totally clean from
totally
chemical
clean.
impurities.
Yes. And then we do other stuff here. These are the hot plates, depending upon where we want to anneal. So there are certain processes that can be performed outside, like in ambient, we still have oxygen here. But then there are things which require special care, especially there are already so many variables, we have different components. So we don't know what is happening and where it is happening. That's why we need this control environment.
Okay.
This thing here is called the glove box.
Glove box.
Glove box. If there are
box.
gloves,
Okay.
and it's a box, so it's a glove box.
Glove box.
And we have series of glove boxes
Yeah,
here, as you can
yes.
see. Everything has different purpose. So remember I mentioned about the thermal deposition unit. So this is the chamber which goes into vacuum. This is the back side of it, and whole lots of arrangement. Two different kinds of pumps are needed because there are certain pumps which will perform only at lower vacuums. So this is called turbo pump.
This is where you deposit the metal.
Yes.
Metals.
Wow.
Wow.
All aluminium, gold, and everything. So we take it into the vacuum and then we deposit.
How
metal.
do you feed it? You feed it the plate from here.
That I'll show you. That's
Okay.
from the front side.
Okay,
This is here
right.
because you can see the volume and shape
Right,
of it.
Right.
And
This lowers the pressure.
this is the control system
Okay.
because it has transformer to control. Because even when we are depositing, there are places. We call it boat where we keep our material, and it needs to be heated at a particular temperature.
Okay.
So that control is given electrically. So that's the entire control for it. Also, it is connected to the pump system, so that we can start the deposition process.
Interesting.
These are another set of glove box which we try to customize and
Okay.
make it on our own with the
Trial
help
and
of
error, okay.
one of our seniors who got so fascinated by working with these things, because while working in the labs there will be some downtimes. So apart from the research what people are doing, typically they will catch up some other skills. Like why not open a company like making these devices, like
Nice.
making these systems,
Nice.
these machines.
Nice side product.
Yes. And this is the sputtering unit.
Sputtering.
Sputtering, what I mentioned, like so
sputtering?
ITO, if we don't purchase this commercially, we can deposit it. So this is entirely different process. And this
sophisticated
is
lab.
oven. Like if there is some process that can go for even higher temperature, so it can go, let's say 500, 600. But for perovskite, typically the process temperatures are low, but for few processes it can take some time. And we have a lot of electronic characterization instrument That one particular is called the impedance spectroscopy.
What it does? Conductivity.
Okay, so as the name suggests, it measures the impedance. So impedance is the part of, any electrical circuit will have resistance and the admittance part, which will have capacitance and inductance. So we make use of these information to analyze our results, like what could be happening, because we cannot see from our eyes. When I say there is ions are moving or some redox reaction is happening, so these are the tools that we use to probe.
Understand the material.
Yes.
What is this supercomputer?
Looks like this is our electrical characterization thing from the back side, and this is the box for the control of this thing.
Wow, it looks like.
And this is the base. This is the main facility. That's what we need, and this itself is in crores.
Okay,
because
it looks
it's
that
a very
way.
it's a very sophisticated thing. What is inside this is very different from outside. This is completely nitrogen. Only few traces of oxygen and moisture that we can see. Like very few parts per million. So if there are million molecules of nitrogen, there are
one part of oxygen.
Just one, or actually we need even less. We need around 0.1, less than 0.1 parts per million of oxygen.
You're protecting against the material from oxidation.
So yeah, it is challenging to maintain that level, and we have our own nitrogen generator. So this is the spin coater I was mentioning. I have few functional videos that I can share, but
the spin coater, that's where you deposit perovskites to the substrate.
Yes. So maybe there are always solutions. So you see there are multiple chemicals bottles. There are several bottles. So like those materials are soluble in one or the others. Then we do the processing.
Wow.
So typically, like if we have some process in light, we'll use this thing. Where
this is the spinner.
The spin coater. So we keep our substrate here. So we give our, see, this is rotating. So depending upon how we rotate, so we typically keep things here. We dispense a solution at a particular instant, dispense it.
You place it on the hole in the middle?
We place our substrate here.
Okay.
Probably I should show the substrate also.
Okay.
So, but this is this is the spin coater, and I'll show you the complete device as well.
Okay.
This is a perovskite. Very less
liquid
is left.
perovskite?
Yeah, liquid perovskite. I'll have
that's
something.
how the perovskite looks. I always wanted to see the perovskite.
This is a perovskite material.
Wow. Okay.
You see, this is the magical transparent looking material.
What's the composition?
This will be some methyl ammonium lead iodide and bromide mix. So this is how it is.
And this has a capacity to reach 22%.
Yeah. So that's a treatment. So the first thing is like some layer deposition. I'll show you some substrates. Maybe there they are. So we have our boxes, like whatever devices we have made. Like that is my box.
Oh, Apoorva, Kelvin.
Yeah, those are my lab mates. This is some other material, but you see the metal is being coated.
Right.
You can see it's like a mirror.
Oh, it's not okay. It's coated.
It's
full circuit.
It's a fully coated. It's for some other purpose, but this is the substrate.
Substrate with the perovskite.
This particular one, I'm not sure. I'll show where I'm sure where it's a perovskite, because there are different people. They work on different aspects. So maybe they might be performing some other things. By the way, these holders are also 3D printed in our lab. So this is my library of devices made over the time.
This is the one with the white band.
Yeah, it includes everything, all the band gaps.
Wow.
Oh, in fact, I have some samples that I bought from my other lab in US as well.
Okay.
So maybe I'll show you the difference. So these are the wide bandgap perovskite.
Wow.
It also includes the one with that relatively high efficiency. So, but these are the typical substrates. As you can see, this is wide bandgap. Like this is 2.3 bandgap. I can see by just looking into the colors. So you can see the metal is there only at dedicated places.
Right.
And it's glass. So that thing, this defines our thing, like our active area. So if you see here, These things will be our devices,
Okay.
and this is the complete substrate. So this particular one has 6 devices: 1, 2, 3, 4, 5, 6.
Right.
And so we connect one probe here, one probe there. So basically, we complete the connection and then test it. And similarly,
So that
this-
means 6 cells inside a substrate?
yes,
Okay.
we can customize this. These are individual cells. We can also make modules,
Okay.
but then the design will be different. And you saw one color, right? Now see another color.
That's a different band gap.
Yes, that's a different band gap. This one is 1.55, the classical perovskite. So this is the perovskite
CH3 NH3
solar cell. Yes.
PV3.
Yeah, and the top thing is gold. So this is a NIP device,
Oh.
and you can see. So we shine light from here.
Okay.
So this will block the light, and this is ITO.
Now the
Yeah,
photons
can
are
you see?
bumping into
Yes.
the substrate, into
Substrates
the perovskite.
and the whatever, and we apply one bias just to characterize it and see how much currents we are getting, and also the fill factors and other things. So this
So
is
you
the,
connect the sensor to the gold plate.
we
to
connect
see
the
conductivity.
connectors,
Okay,
and then we have electrical equipment.
connector is inside this chamber itself, or you have
Yes,
to go to the.
no, inside the chamber. That's the thing. That's the speciality here. Like we can not only make the devices, we can also measure it well inside in the controlled environment. You can read out. You see the oxygen and STO ppm parts per
Wow,
million.
Okay.
So
parts per
so
one
ideally
point.
it should still be less, like 0.1, but still it's decent.
This is the atmosphere of the atmosphere inside.
Atmosphere difference. It's a delta P, like inside and outside.
Right,
but
right.
O2 you see ppm. It's just
Right.
1.5 particles in
Million.
because these things are sensitive. That's why
Right,
even after days,
right.
actually these films are still not degraded, though they have been there for more than 1 year now. Because I wasn't here.
Okay.
So these are the old devices. So I can compare their rest stability and other
Stability
things.
is there.
Yes.
How do you measure the electrical activity? Like, do you have the sensor to measure the?
Okay. So the way we do it, we connect it through the probes. Say these are the probes. These are the connectors which are connected to the instrument. So say we put it like this. In fact, nowadays we have a chuck like customized for our devices.
Oh, nice.
So we can just place it, we can rotate like which one we want to measure, and we can measure it. But like at the
Let's
basic
see,
level,
we can see the measurements now. Present this light. Okay, this light.
we can measure, but they are pretty old devices. But the way it goes,
Okay, wow.
we connect it to these terminals.
Completed the circuit.
Yes.
Takes a lot of patience, to handle these
Yeah,
things.
that's when it gets challenging, when you spend hours, days, and once you characterize and you don't get things,
Right.
then it requires some motivation. But if you do things correctly and you see, so it's a cumulative efforts.
Right.
That's why it takes time to complete a PhD also. Once it is here, we'll keep it here.
Oh, that will shine some light.
Yeah, so the thing we have at the bottom is called the solar simulator.
Sunlight.
Yes, so it simulates the sunlight because people will be doing measurement throughout the world at different parts.
Right.
So, but we should, there should be one uniformity.
Right,
So there is
right.
one standard light which is 100 milliwatt per centimeter square, and it's called one sun. So it's like when sun is at a particular angle, at a particular level.
That is
so what's
standardized
the light?
across the
So that's
labs.
standardized across the labs. So we'll have to calibrate it for the heights and everything. So we have a calibration unit. So once everything is
on
all
it.
right, we'll switch on it.
Yes. Nice.
So
This
now
is
it's
sun.
this is sun.
Sun simulator.
Simulation. So when we say efficiency, so this is my P in. Now I'll see the current, like what is my P out.
Right. So let's see the reading. Where do we see the reading?
Reading, I'll have to switch on other things.
Oh, okay. Systems.
Yeah, and
Okay.
so I
Is
mean,
it possible to see? It's gonna take time.
it's possible, but I mean, it takes some time because it will take some time to initiate.
Right,
But it's
right,
possible.
right,
It's
right.
not a very difficult thing. We keep doing it.
I just want to see how you guys take up the reading, and I'm
Yes.
kind of curious about that.
So this is our entire electrical setup.
So that system is where you get the information
Yes.
about.
So this is the all the electrical things. My devices are still inside the glove box. But I can have their control from the outside, like depending upon.
You take the reading from here.
Yes, we take the reading from here. Actually, we can operate it from the inside as well. This one mouse and other thing.
Right.
Suppose we are working and if we want to do, but it does help to do it here and there. Yeah.
I mean, is it connected to the internet or is just offline?
This is connected to the internet, but not everybody can access that.
Okay.
Like this system and the data is the way the data is transferred.
Completely interactive test environment.
Yes, so this is one interactive environment. We have our special program for perovskite specifically.
You can store data as well here.
Yes. So the way it is done, we give signals. Say, for example, if you see here, the starting one is 0.1 and the stop one is 0.7.
Okay.
So I can change it depending
Change
upon
the
the band gap.
voltage?
It's like suppose I want to do it like if I know my material is mappy, so its band like VOC is around 0.9 and 1. So I keep it that keep a upper limit, then do it. Right now it's not connected specifically, but I'll do a blank run. So this is from one of these solar cells, some material, some testing, and when I run it, so it will start testing. If it's open, it will show something. So if I go to sheet, see it's still recording something.
Oh,
So these are the values, the live readings.
of electrical conductivity.
Yes, like what's connected here. So currently it's kind of open, some system. So, but this is how the measurement is taken. Maybe let me try connecting the actual device
Okay.
for the purpose.
I want to see the efficiency number here. We can read the efficiency number here.
Okay, but I'm not sure. I mean, which cell are what because
Yeah,
I've been away. But
Yeah, that's fine. That's fine.
yeah.
We keep hearing about efficiency.
Yeah.
I just want to see where the efficiency.
Yeah,
has been
maybe
there.
we can take one degraded cell.
Yeah.
So maybe even.
What are the probes made from? Copper.
Different of them use different things. So this contact is copper. We'll see, or I can show you the numbers, like from some of the other data which is stored here. So. So we have connected one of the cells. I hope this is the correct one. Let's see. I've just picked a very random device, maybe 2 years old.
Just want to see the reading, how you do the reading.
Yeah, it's working.
Okay.
Oh, see, I picked a random cell.
Oh, this is the curve.
This is the curve, and this is 17.3%.
Okay. Oh,
Okay, so after all, it's not that bad. Its
not
VOC
degraded,
is 1.0. This cell I made at least 1.5 years back.
Okay.
Since it was kept inside the glove box, controlled environment, this
Okay.
did not degrade. I told like the
17%.
it's an old device.
Nice. 1 year old. 1.5 year old.
Yes. And this is the fill factor 72.
Okay.
Okay, maybe I should remeasure my devices. I literally, after I came back from US, I just picked.
You mean those are the stable ones?
I mean, I'll have to check. They may be 20% 1.5 years back. Now they are 17. But I'll have to tally. But this is 17.2%.
Just 3% decrease in efficiency.
I don't know. Like, it could be just 18 or they might have stayed. But this is a working solar cell. Now you see the hysteresis part I was talking about. So this is one scan. Here you see this is slightly better.
Right.
This is slightly lower.
Right.
And
So you take the mean of it, right?
No, we take note of both the values because that's a difference. You remember that analogy of the table I was referring to? The same insect trying to move from one end to the other.
Current flow, right?
Yes. So these are the values. So this VOC is 1.08.
Okay.
Its short circuit current is 22 milliwatt per centimeter square because 10 to the power 1, it's 22. And efficiency is 17.29. It's a working device.
Right.
See, that's the thing. So
What's the material again?
it's a regular MAPI.
MAPI, okay.
CS3, NS3, PB, I3, and IP structure with gold on top of it.
Still
1.5 years old.
17%.
So, yes.
If you had kept that device not in this chamber, somewhere in the outside, it would have degraded, right?
We do perform that study as well. So we have separate light source optimized for one sun. Probably I can just plug in one of them. Or this is the light source.
You conduct study here?
Yeah, so we keep it like it's an ambient. So we have this setup which can probe currents every 10 seconds.
Okay.
So if we continue running for days or week, we'll get the data. So like degradation, like how it is degrading. Now we can create those environment like specific light, specific temperature or other things, and we can carry out these degradation studies, the targeted degradation studies. Okay, it's good that we get to see this.
I saw the enthusiasm in your face.
Because it's 1.5 years. Yes, it's an old device. That's why I see the perovskite has hope.
Right.
So if we solve other problems, this is encouraging. If you see the old data, I picked a random device. I could have picked any device, and it works. So that's the thing.
It's not carcinogenic, right?
Right now it's not, but you better wash your hands soon.
Just kidding.
Yeah. So as you can see, so this is the characterization, and we can connect other device. Like for example, others might not be that efficient in the same substrate. So maybe since we are doing, can you do one thing?
Yes.
Can you just keep clicking this part? You sit here.
Play.
You just click here when I say.
Okay. Yes.
That means I'm connecting another device.
Okay.
So I'm hoping the others won't work as well.
Okay.
Because it's an old device. So we have a chuck, but I'll just do old school way for now. Okay, can you click it?
Yes.
Now just wait.
Let's take another reading.
You see, so
purple one.
Different cell. So we can compare.
Okay, it's taking.
So here the field.
Where's the data?
Okay, so data is this, but it's not yet updated.
Okay, so it's going to take time?
No. So we'll have to see that, give the instruction that you update. So now this one is only 13%.
So what did, okay. Lower it is, higher the efficiency.
Yeah, also the fill factor. The previous blue one was 72 fill factor.
Okay.
There VOC and currents are still okay. See, the currents are still okay. VOC is still kind of comparable, but the real killer is fill factor. That's why the efficiency went down from 17 to 13.
Same material or this is
same material but different device. So that variation should be. So ideally we want that everything should be same.
Right.
But there are multiple factors like see they are
and when
so
you
sensitive.
Carry efficiency, you take the average of all the 6 cells
Yes.
and take the mean of this.
Yes.
Right? Okay.
And also there could be some physical scratches and all those things, so
Yeah,
we'll have to
yeah,
discard
right,
it.
right.
But yes, ideally we'll have to, that's why we see a spread. So this
Right.
spread should be minimum. Okay, can you click that button again?
Yes, yes,
Just,
yes.
Yes, this one.
It's taking now which color?
This one
it's
is working
giving
fine.
16. My guess is 16.
Okay, yeah, I think so.
So
Wow, 16.12.
yes.
So it's fairly close. That's acceptable. So these are the real perovskite solar cells which are getting
Nice.
measured.
Lovely
2
to
years
see
old
in action.
in action.
I mean, I just saw the graph you showed me there. Now it feels good to see.
Okay, can you press once again?
Yes, yes. Now which color? Oh, it's 15.
But it's fairly close. And after
Yeah.
2 years,
I think you can
we
take
just
the
had
average,
one lower device which is still working. But still, I'm happy to see them working even after years.
1.5 years.
So, but this is inside the glove box.
Right.
And if I put it under continuous light, it will degrade fully in 72 hours. Can you press once again?
Yes, yes.
So I'm making you do some of my work. So characterizing.
Now which color? Oh, 60. No. 15.5. 16.
16.12. Only one device was away, so this is the last one. Can you measure? So all of them work.
70. No. Yeah, 16.5.
So okay,
17.5.
So 72 fill factor. So this is a decent substrate. Only one was off. So
mean
statistically around 60. So 1 year old device and other thing. So it's working. So it's a working solar cell. And now you know what I was talking about, the hysteresis and the other things.
Right. Cool. Thanks for showing.
Yeah, I didn't expect that I will be able to see it. But yeah,
Working
even
time.
I'm happy to see some of the cells working.
Nice.
Seeing 17.5 even after 2 years, it feels amazing. You see this?
Yes.
You see that's blanket and this is the mask. That's how we make sure that the metals gets deposited only at certain places where we want and where we don't want.
Got it.
So this goes inside this chamber. I'll open and show you this chamber. This is the entire control system for this. By the way, this itself again is around or more than 1 crore. Just this piece, except the glove.
Just to deposit a metal layer,
Yeah.
that instrument costs 1 crore.
Because it's sophisticated, like we need precision. It quotes in nanometers, 80 to 100 nanometers. So first I'll have to check whether it's in ambient or not, because if it's in vacuum, I won't be able to open it. So currently it's in the atmosphere, this 1E3, and it's not functional. So I will just open just to show. Probably I'll switch on light. Yeah, as you can see inside this chamber.
Okay.
So that particular tray, that tray with mask and substrate, that we put it here. You see, there we keep our metals. Like even right now there is this silver here, and there are some other molecules, organic or something, that we use these crucibles, like holders to place this material, and then it gets deposited. And these are the sensors to sense how much material is getting deposited.
Okay.
So they are a particular kind of QCM sensor.
Cost 1.5 CR.
Yeah, around, and more sophisticated one, more bigger one. Like if you don't want to do by spin coating, you want to do all deposition, you need to have broader control, like many people do. So these are things. See, this is in the lab stage. So imagine that's why the pilot is around that.
200 CR.
Yeah, but the good things, all those people who work here in such environment, they are well trained with this. So I mean, that's why many people choose to go to industries as well. I mean, because people in general are equipped with this, and it takes several hours to reach a certain amount of vacuum. So we'll have to wait, we'll have to be patient. Then to deposit, we control from here. So that entire process takes around 2 days.
Whoa,
because
metal deposition takes 2 days?
No, metal deposition will take like say 1 to 2 hours for reaching vacuum, 1 hour for coating, then again waiting so that
where
we
do
can
you wait? Like you kept the metal for deposition?
We'll do some other work.
Okay.
Or if we are coating, we'll have to be here. We'll have to monitor, just like driving. But yes, coating and then annealing, like heating at some point. So it requires a lot of patience.
Oh my God! For multiple.
You can see the box are full. I have 2 such boxes, and I have some other devices. Like they are shaped differently, as you can see. This I got it from my other lab, US lab. I wanted to perform some degradation test. I hope they will also work at some point, but their geometry is slightly different, so I'll have to figure out a way
Got it through the flight?
Yeah, I got it through the flight. See, so they are shaped differently.
Wow.
So probably I'll switch on this light now because the characterization for this substrate is done.
Yes.
And the data is automatically saved.
Yes.
And this is the data. I'm happy that they worked.
Yes, I'm happy that
that you got to see. Yeah. So probably.
I think we're done with this.
Yes.